Right now, as you lie there, iron is working inside your body. Real iron, the metal, atoms of it carrying oxygen through your blood at this very moment, from your lungs to every cell. Hemoglobin, the protein that makes blood red, holds an iron atom at the very center of its molecule. Without that atom, you would suffocate within minutes. And here is what makes that interesting. This iron did not come from Earth. Earth cannot make iron. No planet can. Iron is forged in only one place in the entire universe, in the core of a dying star, in the fraction of a second before that star explodes. A star 10 or 20 times more massive than our Sun lived out its life, burned through its fuel layer by layer, and in the final moment, when its core collapsed, when pressure and temperature hit limits that are difficult to express in numbers, that is when iron was created. Then the star blew itself apart, scattering its material across interstellar space. That material drifted for millions of years through cold and silence, until it ended up in a cloud of gas and dust, from which our Sun, our Earth, our oceans, and eventually you, were made. The iron in your blood is older than the Sun, older than the Earth, older than the entire solar system. It carries the memory of an explosion that no human ever witnessed because humans did not exist yet. Planets did not exist yet. There was only a cloud. And here is what is remarkable. From that one cloud, from the same mixture of hydrogen, helium, dust, and frozen molecules, 8 completely different worlds were born. One became a scorched rock with no air. Another became a blazing furnace with pressure strong enough to crush a submarine. A third became the only place where atoms learned to think about themselves. A fourth became a cold, rusty desert that may once have been fit for life. A fifth became a ball of gas so enormous that over 1,300 Earths would fit inside it. A sixth became a world wrapped in rings made of billions of ice fragments, each one flying along its own tiny orbit. A seventh became a planet lying on its side, as though something knocked it over. An eighth became an ice giant at the edge of darkness, where sunlight is 900 times weaker than it is here. One recipe, one cloud, the same ingredients: hydrogen, helium, oxygen, carbon, nitrogen, silicon, iron, and 8 completely different outcomes. How did this happen? What exactly turns the same molecules into a molten hell on Venus and a blue ocean on Earth? Why did Mars, which started its story almost the same way our planet did, with rivers and possibly lakes, lose everything, while Earth kept its water and its air? Why did Jupiter become a monster 318 times heavier than Earth, while Mercury stayed a tiny, scorched cinder? And does this story have anything to do with you personally? Yes, directly. Here is why. The calcium in your bones was produced inside a star several times heavier than our Sun, a star that exploded before the solar system even existed, flinging its material across light years. The oxygen you are breathing right now was released into the atmosphere by microorganisms that learned to split water molecules using sunlight 2.5 billion years ago, a process we call photosynthesis. The water in your cells may have been delivered to Earth by a comet or asteroid that flew in from beyond the frost line 4 billion years ago. The nitrogen that builds your proteins was captured by Earth's atmosphere from volcanic gases and held in place by the gravity of a planet that happened to be massive enough not to let it escape. Every atom in your body traveled a path that began in a star, passed through an interstellar cloud, a protoplanetary disk, an asteroid bombardment, an ancient ocean, billions of living organisms, and ended up here, in this room, in you. You are literally, without metaphor, made of the same material as Mercury, Jupiter, and the comets in the Oort Cloud. The difference between you and the rusty desert of Mars comes down to distance, mass, and a handful of chemical forks in the road where fate went one way instead of another. Everything you feel right now, the weight of the blanket, the cool air, your heartbeat, all of it exists because our planet ended up at the right distance from the right star, with the right mass and the right chemistry. Move Earth a little closer to the Sun, and we would have gotten Venus. A little farther, and we would have gotten Mars. A bit less mass, and the atmosphere would have leaked into space. A bit more, and the planet would have started pulling hydrogen from the disk and swelled into a gas giant. The difference between your existence and a dead wasteland is a difference in distance, in mass, in a few chemical reactions that went one way rather than another.
Tonight, we are going to walk through the entire solar system, slowly and in detail. We will start with the cloud from which everything was born, and we will see how temperature and distance split one set of ingredients into two fundamentally different kinds of worlds. We will look at what happened to each of the 8 results of this cosmic experiment, and why each one became what we see today. And we will find that the story of the solar system is really the story of one question that nature asked itself 4.5 billion years ago. What happens if you take the same ingredients and change the temperature, the pressure, and the amount? But there is more, because behind the story of 8 planets lies a deeper, more personal question. If everything, Venus and Earth and you, is made of the same material, if the difference between hell and paradise comes down to distance and mass, then how many other such experiments are running right now around other stars? How many clouds collapsed into disks? How many disks produce planets? And on how many of those planets did distance and mass line up as luckily as they did here? We have only started finding answers to these questions in the last 30 years, with the discovery of thousands of exoplanets, worlds orbiting other stars. And the answers we are getting are changing everything we thought about our place in the universe. We will talk about all of this, slowly, step by step. No rush, no skipping details. Because here, the details are not a distraction from the point. The details are the point. Settle in. We begin at the very beginning, with the cloud. Before we dive into the physics, it is worth pausing to think about something. People have been looking at the night sky for thousands of years, noticing that certain lights move differently from the rest, calling them planets, wanderers, and trying to understand what was going on. The first 2,000 years of that effort were a story of brilliant wrong turns. Earth at the center, perfect circular orbits, epicycles stacked on epicycles, crystal spheres. Then, in roughly 200 years, from Copernicus to Newton, the picture flipped. Earth was just another planet. Orbits were ellipses. And one equation, the law of universal gravitation, explained falling apples and the motion of Jupiter alike. Another 200 years, and Einstein showed that even Newtonian gravity was an approximation, that mass actually curves space-time, and planets travel along the shortest paths through that curved geometry. And then, within living memory, we started sending robots to the planets and seeing them with our own eyes. Volcanoes on Io, methane lakes on Titan, icy geysers on Enceladus. Everything we discuss tonight is the result of this relentless 5,000-year effort. Observe, record, get it wrong, fix it, observe again. And here is the current picture.
4.5 billion years ago, the solar system did not exist. In its place, there was a cloud, a vast, loose, cold accumulation of gas and microscopic dust particles stretching across trillions of miles. If you could have seen it from the outside, it would have looked like a dark nebula against the background of distant stars, roughly the way the Orion Nebula looks today. The Orion Nebula sits about 1,300 light-years from us. Inside it, new stars are forming right now. When astronomers talk about how our solar system came to be, they are not speculating from scratch. They look at nebulae like Orion and see the same process happening in real time around other stars. Our cloud, often called the solar nebula, was made mostly of hydrogen and helium. These are the two most abundant elements in the universe, and they made up roughly 98% of the cloud by mass.
The remaining 2% was everything else. Oxygen, carbon, nitrogen, silicon, iron, magnesium, sulfur, and several dozen other elements in trace amounts. All of those heavier elements, everything heavier than helium, did not originate in our cloud. They were produced by earlier generations of stars through thermonuclear fusion in their cores, through supernova explosions, through neutron star mergers. Our cloud was recycled material. It contained the ash of dead stars. 2% might sound like nothing, but those 2% created everything you stand on, everything you breathe, and everything you are made of. Hydrogen and helium, despite being 98% of the total, are too light and volatile to form solid bodies near a hot star. They can become part of a planet only in cold, distant regions, where the gravity of a gas giant is strong enough to hold them.
But those 2% of dust and heavy elements, silicon, iron, oxygen, carbon, those are what became the rocks that stuck together into planetesimals, that collided and merged into planets, one of which you are lying on right now. So, the cloud existed. It was cold, roughly 10 to 20 degrees above absolute zero. It was incredibly thin, with a density so low that the best laboratory vacuum on Earth would feel thick by comparison. And it was stable. The internal gas pressure balanced the cloud's own gravity, and it could have drifted like that for millions of years, producing nothing, simply existing as part of the galactic landscape. But then something disrupted the balance. We do not know exactly what. The most likely scenario is a supernova explosion nearby. There is even specific evidence for this. Meteorites contain traces of short-lived radioactive isotopes, aluminum-26 and iron-60, that can only be produced in the explosion of a massive star, and that decay within a few million years. Their presence in the oldest solid bodies of the solar system means they were injected into our cloud immediately before or during its collapse. In other words, the birth of the solar system was probably triggered by the death of another star. We are the offspring of someone else's explosion. The material we are made of includes not only the ancient ash of long-dead stars, but also fresh debris from a supernova that went off right next door and nudged our cloud into collapsing. The shock wave from that dying star passed through the cloud, compressed certain regions, and in those denser patches, gravity began winning against pressure for the first time. The region started to collapse, to squeeze inward under its own weight.
And here is where the physics that explains almost everything we will see from now on begins. When a cloud collapses, it spins faster. This is not magic and not coincidence. It is the conservation of angular momentum, the same law that makes a figure skater spin faster when she pulls her arms to her chest. The cloud always had some rotation, however slight, because nothing in the universe is ever perfectly still. But as it shrank, that rotation intensified. And the rotation did something critically important. It prevented material from falling toward the center equally from all directions. Material falling along the rotation axis, from above and below, could drop freely toward the center. Nothing stopped it. But material in the plane of rotation could not fall straight in, because centrifugal force held it in orbit. And so the cloud did not collapse into a ball. It flattened into a disk. Think of pizza dough being spun in the air. It stretches, it flattens out. The same thing happened to our cloud. At the center, a dense, hot core, the future sun. Around it, a spinning disk of gas and dust, thin relative to its diameter, hot near the center, and cold at the edges. We can actually see such disks around young stars right now. The ALMA telescope, a radio telescope array in Chile's Atacama Desert, captured a stunning image in 2014 of the disk around a young star called HL Tauri, roughly 450 light-years away. The image shows concentric rings and gaps, structures that are most likely carved by forming planets clearing their orbits. We are looking at a planetary system in the act of being born. Our solar system looked roughly like that 4.5 billion years ago, and similar disks have been found around hundreds of young stars. Planet formation from protoplanetary disks is not a one-off event that happened only to us. It is a routine, ordinary process that occurs throughout the galaxy wherever new stars form. This disk is called the protoplanetary disk, and every single planet, every moon, every asteroid and comet in the solar system was born from it. It is worth pausing here to think about the scale. The protoplanetary disk had a diameter on the order of several hundred astronomical units. That is tens of billions of miles. By interstellar standards, it is tiny. The nearest star, Proxima Centauri, is hundreds of thousands of astronomical units away. But by the standard of anything familiar to us, it is an enormous space. Light crosses the disk in a few tens of hours, and across that entire territory, from the scorching center to the icy edges, the same process was underway. Dust grains sticking together, growing, colliding, breaking apart, growing again. Billions of small collisions, each individually insignificant, and together they built worlds. The chemistry of the disk deserves a mention because it is what determined the flavor of each dish in our recipe. Close to the sun, only the most heat-resistant minerals could condense. Aluminium and calcium oxides, silicates, metallic iron, and nickel. These substances made up what are called the first condensates, and they are found in the oldest inclusions discovered inside meteorites. Calcium-aluminum-rich inclusions, or Ca1s. Radioisotope dating of these inclusions gives an age of 4,567,000,000 years, the oldest solid material in the solar system, a kind of moment zero from which the age of everything else is measured. As you moved farther from the sun, the range of available solid materials expanded. Hydrated minerals appeared, silicates that had trapped water in their crystal structures. Organic compounds appeared. Ice appeared. And each additional ingredient increased the amount of building material available. This is why the frost line became such an important boundary. Beyond it, there was several times more solid material available, and that gave the cores of the outer planets a crucial head start. Now here is the critical fork, the one that split one recipe into two fundamentally different types of worlds. Picture the disk as a pan that is searing hot in the center and icy cold at the edges. Close to the sun, temperatures are so high that only the most heat-resistant substances can exist as solids: silicates, metals, oxides.
Everything else, water, ammonia, methane, carbon dioxide, evaporates here and stays as gas. And gas, as we said, is too volatile to clump into planetary seeds. So near the Sun, the building material for planets is limited, rock and iron only. But farther from the Sun, beyond a certain boundary, the temperature drops low enough for water and other volatile substances to freeze. They turn into tiny ice crystals that can stick to dust grains, multiplying the amount of available solid material several times over. This boundary is called the frost line, or snow line. In our solar system, it sat at roughly 2.5 to 3 astronomical units from the Sun, between the orbits of Mars and Jupiter. 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. The frost line is an invisible line that no telescope can see. It has no physical form, no wall, no barrier. It is defined purely by temperature. At a given pressure and distance from the Sun, water transitions from gas to solid. And this invisible line determined the architecture of the entire solar system. On this side, small, rocky, dense planets. On the other side, giant worlds swollen with hydrogen and helium because their icy cores managed to gather enough mass to capture gas from the disk.
Let us walk through this process step by step, because it is beautiful, and it deserves to be seen in detail. At the very beginning, when the disk had just formed, the solid particles in it were microscopic, dust grains a fraction of a millimeter across. They collided at low speeds and stuck together. The forces holding them were tiny. Electrostatic attraction, Van der Waals forces, the same thing that makes dust cling to furniture in your room. From dust grains came clumps. From clumps came pebbles. From pebbles came boulders. The process was slow and difficult, and it had its own challenges. At a certain stage, when objects reached roughly 3 feet across, they started bouncing off each other during collisions instead of sticking. This is the so-called meter barrier, and it puzzled planetary scientists for years. How did dust grains jump from inches to miles? The most likely answer: through gravitational instability within the disk itself. When the density of dust in certain zones of the disk reached a critical threshold, those regions began collapsing under their own gravity, skipping the intermediate stages. Instead of growing slowly, pebble by pebble, mile-sized bodies called planetesimals were born all at once. And once planetesimals appeared, everything changed. Because a mile-sized body already has noticeable gravity of its own, it pulls surrounding debris toward itself. The larger it gets, the harder it pulls, the faster it grows. This is called gravitational focusing, and it turns linear growth into exponential growth. Large bodies grow faster than small ones because they intercept more material. From planetesimals grew protoplanets, planetary embryos the size of the Moon or Mars. And here is where the frost line did its decisive work. On this side of the line, in the hot inner zone of the disk, protoplanets grew from rock and metal.
There was relatively little of this material, remember. Heavy elements made up only 2% of the original cloud. So what formed here were small, dense, rocky worlds. Mercury, Venus, Earth, Mars, they all grew from this modest ration of rock. None of them reached a mass sufficient to capture hydrogen and helium from the disk. But beyond the frost line, the picture was completely different. There, in addition to rock and metal, there was ice, water ice, ammonia ice, methane ice. The total mass of available solid building material increased roughly 3 to 4 times. Protoplanets beyond the frost line grew faster and larger, and when the mass of a core reached about 10 Earth masses, a tipping point occurred. The core's gravity became strong enough to start pulling in hydrogen and helium directly from the gas disk. And hydrogen and helium are 98% of everything.
It is as though you were building a house out of bricks. And suddenly, your house became so large that it started pulling in all the surrounding air and growing a shell of it. This process is called runaway gas accretion, and it is incredibly fast by astronomical standards. In a few 100,000 years, a blink compared to the age of the solar system, a core of 10 Earth masses acquires a massive envelope of hydrogen and helium and transforms into a gas giant of hundreds of Earth masses. That is how Jupiter was born. That is how Saturn was born. The same recipe, the same cloud, the same elements, but different temperatures at different distances from the Sun produced fundamentally different types of planets. Here is something worth emphasizing, something we will come back to again and again throughout this story. The physics behind all of this is simple. Gravity, temperature, composition. No exotic forces, no mysterious mechanisms, just hotter near the star and colder farther away. Just heavy things sink and light things float off. And from these three variables, distance, mass, chemistry, all the dizzying diversity of our planetary system is born. But the disk's story does not end there. The young sun was doing something else. It was shining with increasing intensity. Its ultraviolet radiation and the solar wind, a stream of charged particles flying from the star at hundreds of miles per second, were gradually blowing the gas out of the disk. The disk was dissipating. And there was a hard deadline. Roughly 5 to 10 million years after the sun's birth, the gas in the disk was essentially gone. Blown away. Swept out by the star. Dispersed into interstellar space. 5 to 10 million years. That is how long protoplanets had to build up mass and capture hydrogen and helium. If a core reached critical mass before the gas vanished, it became a gas giant.
If it did not make it in time, it stayed what it was, a rocky or icy core with a thin atmosphere or none at all. Uranus and Neptune are exactly this intermediate case. They formed far from the Sun, where the disk was thinner and orbital periods were longer. Everything moved more slowly. Their cores grew more slowly, and by the time they reached a mass sufficient to capture gas, the disk was already dissipating. They managed to grab some hydrogen and helium, but far less than Jupiter and Saturn did. That is why Uranus and Neptune are much smaller. They are sometimes called ice giants, as opposed to the gas giants Jupiter and Saturn, and the name accurately reflects the difference. Uranus and Neptune are made primarily of water, ammonia, and methane in various exotic states, with hydrogen and helium forming only their outer shell. So the disk dispersed. The Sun is burning. 4 small rocky planets orbit close to the star. 2 gas giants and 2 ice giants orbit farther out. Between them, a belt of debris that was never allowed to become a planet. Beyond Neptune, a vast ring of icy bodies left over from the edge of the disk. It would seem the system was formed, everything in its place, but in reality, the most interesting part was just beginning. Because the planets did not simply sit on their orbits and wait. They moved. They migrated. Jupiter may have drifted closer to the Sun and then swung back outward, ploughing through the inner disk like a tractor through a field. Neptune was probably flung onto a distant orbit, and as it tore through the belt of icy bodies, it showered the inner system with a rain of comets and asteroids. But we will talk about that later, when we reach the gas giants and their violent youth. For now, we need to get to know the thing at the center of it all. The thing that lit this recipe on fire and has been keeping it burning ever since. But here is what you should carry into the next chapter. That central fire is not constant. The sun, 4 billion years ago, was 30% dimmer than it is today. And the sun a billion years from now will be bright enough to boil Earth's oceans. The engine that drives all 8 worlds is itself changing, slowly, steadily, and everything we are about to see, every atmosphere gained or lost, every ocean kept or evaporated, is a response to that changing engine, the sun. The sun is so familiar that we almost stop noticing it. It rises, lights the day, sets. We plan our schedules around it, wear sunglasses because of it, put sunscreen on our skin. But we rarely think about what it actually is. And we should, because without understanding the sun, it is impossible to understand any of the 8 planets. The sun is not a lamp hung in empty space for the planet's convenience. The sun is the engine that determines everything. Temperature, atmospheric chemistry, the boundaries of habitability, the fate of magnetic fields, the rate at which atmospheres are lost, even the shapes of orbits. Every planet in the solar system is an answer to the question, what happens to material sitting at such and such a distance from such and such a star? Let us look at how this engine works. The sun is a ball of superheated plasma, roughly 865,000 miles across. If Earth were a pea, the sun would be a fitness ball. It contains 99.86% of all the mass in the solar system. All 8 planets, all their moons, every asteroid, every comet, all the interplanetary dust, together they make up barely 1/7%. The sun does not merely dominate the system, the sun is the system, and everything else is impurities caught in its gravity. The sun's energy is born in its core, where the temperature reaches roughly 27 million degrees Fahrenheit, and the pressure is 250 billion times the atmospheric pressure on Earth's surface. Under those conditions, hydrogen atoms move so fast that they can overcome the electrical repulsion between their nuclei and fuse together. 4 hydrogen nuclei, 4 protons, merge into one helium nucleus, releasing energy in the process. The mass of the resulting helium nucleus is slightly less than the combined mass of the 4 original protons. The difference, roughly 0.7%, is converted into energy by Einstein's equation E equals mc squared. 0.7% sounds trivial, but multiply it by the staggering number of reactions happening every second, and you get an output of roughly 3.8 times 10 to the 26th power watts, a number impossible to grasp. Every second, the sun converts roughly 600 million tons of hydrogen into helium, losing about 4 million tons of mass that fly off as radiation. 4 million tons per second. That is the mass of a small mountain, vanishing every single second. And yet the sun is so massive that over the entire 4.5 billion years of its life, it has lost only about 0.03% of its original mass this way. The hydrogen supply in the core is enormous, and it will keep fueling reactions for roughly another 5 billion years. It is worth lingering on thermonuclear fusion for a moment, because its scale deserves to be felt. We cannot see the sun's core directly. It is hidden beneath roughly 430,000 miles of dense plasma. But we can hear it. The sun vibrates. Convective processes in its interior generate sound waves that pass through the entire star, causing it to pulse like a giant bell.
These pulsations can be observed as tiny periodic changes in brightness and surface velocity. By studying them, a discipline called helioseismology, by analogy with seismology on Earth, scientists have built a detailed model of the sun's interior. Temperature, density, rotation speed at different depths. Helioseismology turned an opaque ball of plasma into an object accessible to detailed study, even though no instrument will ever physically penetrate its core. Energy born in the core does not fly out of the sun immediately. A photon born at the center cannot simply escape.
It is instantly absorbed by the surrounding plasma, re-emitted, absorbed again, re-emitted again. It wanders inside the Sun, bouncing from particle to particle, like a ball in a pinball machine, slowly working its way toward the surface. This takes, on average, between 100,000 and 200,000 years.
A photon needs hundreds of millennia to travel 430,000 miles from the core to the surface. And then, having finally broken free, it reaches Earth in 8 minutes. The sunlight you see when you look out the window in the morning was born in the Sun's core long before Homo sapiens existed. The Sun's visible surface, the photosphere, has a temperature of roughly 10,000 degrees Fahrenheit. It is not solid, of course. The Sun has no solid surface at all. The photosphere is simply the layer below which the plasma becomes opaque. It is a surface only in the sense that it is the last layer from which photons can escape. Above the photosphere lie the chromosphere and the corona, the Sun's outer atmosphere. And here lies one of the most persistent mysteries in solar physics. The corona's temperature reaches 2 to 4 million degrees Fahrenheit. It is hundreds of times hotter than the photosphere beneath it.
That is roughly like walking away from a campfire and discovering that the air 30 feet from the flames is hotter than the flames themselves. Physically, it seems absurd, and the mechanism behind coronal heating is still being studied. The most likely explanations involve magnetic processes, reconnection of magnetic field lines, magneto-hydrodynamic waves, but full clarity has not arrived yet. From the corona, a continuous stream of charged particles flows outward, protons and electrons traveling at speeds between roughly 700,000 and 2 million miles per hour. This stream is called the solar wind, and it fills all of interplanetary space. The solar wind blows on every planet, every asteroid, every comet. Where a planet has a magnetic field, like Earth, the wind is deflected and flows around the planet, creating a magnetosphere, a protective bubble. Where there is no magnetic field, like on Mars, the solar wind crashes directly into the upper atmosphere and gradually strips it away into space. This process is one of the key reasons Mars lost its atmosphere and turned into a cold desert. We will return to this in detail when we reach Mars. For now, remember, the solar wind is not an abstract astrophysical concept. It is a real force that is, right this moment, tearing away the atmosphere of Mars at a rate of roughly a quarter pound per second. A small amount, but over 4 billion years it adds up to enough to turn a once warm, wet world into a frozen wasteland. The Sun also has a complex, constantly shifting magnetic field that creates dark spots on the surface, sunspots, known to astronomers since the early 1600s. The number of sunspots varies on a cycle of roughly 11 years. At solar maximum, the Sun's magnetic activity peaks, solar flares erupt, and coronal mass ejections, massive blasts of plasma and magnetic field, rocket through interplanetary space at up to several million miles per hour. When such a blast reaches Earth, it compresses the magnetosphere, triggers geomagnetic storms and auroras. In 1859, the most powerful recorded geomagnetic storm, the Carrington event, caused auroras visible as far south as Cuba and Hawaii, and telegraph wires sparked and transmitted signals without being connected to batteries. If a storm of that magnitude hit today's Earth, with its dependence on electronics and satellite networks, the consequences would be severe. For planets without magnetic fields, solar activity is an even bigger problem. Every flare, every coronal mass ejection strikes the upper atmosphere head-on, knocking molecules loose. On Mars, stripped of its magnetic shield, every period of solar maximum means accelerated erosion of an already tissue-thin atmosphere. There is one more feature of the Sun that plays a critical role in the story of the planets, and one we rarely think about. The Sun is slowly, steadily getting brighter. But first, let us talk about what this means for habitability in the broadest sense. The habitable zone, the range of distances from a star where liquid water can exist on a planet's surface, is not fixed. It moves. As the Sun brightens, the habitable zone slowly shifts outward. 4 billion years ago, its inner edge may have been closer to the Sun than it is now. A billion years from now, it may cross Earth's orbit, leaving our planet outside the zone of possibility. And 5 to 6 billion years from now, when the Sun becomes a red giant and its luminosity increases 1,000-fold, the habitable zone will jump far outward to the orbits of Jupiter and Saturn, Europa, Enceladus, Titan. Frozen worlds locked under ice shells right now may briefly find themselves in conditions that allow liquid water on their surfaces. Habitability is not a property of a planet. It is a property of the pair, planet plus star, and it changes over time. The solar wind also defines the boundary of our system. The stream of charged particles flowing from the corona travels through interplanetary space, gradually weakening with distance. Where the pressure of the solar wind balances the pressure of interstellar gas, there lies a boundary, the heliopause. Beyond it begins interstellar space, territory governed not by the Sun, but by the galaxy. The heliopause sits roughly 7.5 to 9 billion miles from the Sun, far beyond the orbits of all the planets, beyond the Kuiper Belt. The Voyager 1 and Voyager 2 probes crossed this boundary. Voyager 1 in 2012, Voyager 2 in 2018, and sent back data from interstellar space. They were the first human-made objects to leave the solar bubble. The heliosphere, the bubble of solar wind enveloping the entire solar system, shields us from a large fraction of galactic cosmic rays, high-energy particles streaming from distant supernovae and pulsars. Without the heliosphere, Earth would be subject to more intense radiation, which could affect atmospheric chemistry and possibly biological evolution. The Sun protects us not only with its light and heat, but also with its wind, a stream of particles that creates an invisible cocoon around our system. Now, why is the Sun getting brighter? The mechanism is surprisingly simple. As hydrogen in the core burns and turns into helium, the core's composition changes. Helium is denser than hydrogen. Under the force of gravity, the core contracts slightly. Pressure and temperature increase, and the rate of thermonuclear reactions goes up. More reactions means more energy, means a brighter star.
Roughly 1% brighter every 100 million years. Unnoticeable on a human scale, but relentless on a geological one. When the solar system was young, 4 billion years ago, the Sun shone roughly 30% dimmer than it does today. 30% is an enormous difference. If you took today's Sun and turned the brightness down by 1/3, Earth's surface should have frozen solid. Average temperatures would drop below freezing. Oceans would ice over. But we know for certain that 4 billion years ago, Earth had liquid oceans and probably already harbored life. The geological evidence is unambiguous. Sedimentary rocks, minerals that form only in the presence of water, chemical signatures of biological activity in the oldest layers, all pointing to a warm, wet Earth in an era when the Sun was dim. This contradiction is called the faint young sun paradox, and it was first clearly articulated by Carl Sagan and George Mullen in 1972. The most likely explanation is that the early Earth's atmosphere contained far more greenhouse gases than it does today. Carbon dioxide, methane, possibly other gases, created a more powerful greenhouse effect that compensated for the weaker sunlight. As the Sun gradually brightened, geological processes, The weathering of rocks, the chemical binding of carbon dioxide into carbonates slowly reduced greenhouse gas concentrations, keeping surface temperatures roughly stable even as the energy input increased. This is a kind of thermostat, a geological feedback loop that has operated for billions of years. When the sun shone dimmer, greenhouse gases were more abundant and the planet stayed warm. When the sun got brighter, greenhouse gases decreased and overheating did not occur. But this thermostat has limits. In roughly 1 billion to 1.5 billion years, the sun will be bright enough that even complete removal of carbon dioxide from the atmosphere will not save Earth from overheating. Oceans will start evaporating. Water vapor, a powerful greenhouse gas, will amplify the warming, which will cause more evaporation, and the same runaway greenhouse effect that already killed Venus will start. Earth's habitability has an expiration date. And here is what is important to understand before we move on. The sun we live with today is a middle-aged sun. It is roughly 4.5 billion years old, with roughly the same amount of time left before the hydrogen in its core runs out. In 5 billion years, the core, by then almost entirely helium, will contract further. Hydrogen burning will shift to a shell around the core. Energy output will spike, and the sun's outer layers will expand. The sun will swell into a red giant, growing so large that its edge will reach the current orbit of Earth, possibly past it. Mercury and Venus will be swallowed. Earth's fate is uncertain. As the sun loses mass during the red giant phase, Earth's orbit may widen, and the planet could stay just ahead of the expanding surface. But even if Earth physically survives, by that point it will long since have been a dead, scorched chunk of rock with no water and no air. Then the sun will shed its outer layers as a beautiful, expanding shell of gas, a planetary nebula. The name is a historical accident with nothing to do with planets. William Herschel coined it in the 1700s because these objects looked like the greenish disks of planets through his telescope. In reality, they are the shed skins of dying stars, lit from within by the blazing remnant of the core. If someone were observing our system from outside in 6 or 7 billion years, they would see a beautiful expanding ring of glowing gas, and at the center, a tiny bright point. It would look like the dozens of planetary nebulae we observe today in our galaxy: the Ring Nebula, the Cat's Eye, the Helix. Each one is a memorial to a star that lived a life like our sun's and ended it the way ours will. And at the center, a tiny, dense, hot body roughly the size of Earth, but carrying half the current sun's mass, a white dwarf. It will cool slowly over trillions of years, gradually fading until it becomes dark, cold, invisible. The planets that survive the red giant, probably Jupiter, Saturn, Uranus, Neptune, will continue circling this dying ember. The solar system will persist, but it will be a very different place. Dark, cold, quiet. But all of that is billions of years away.
Today the sun is stable, reliable, and every morning it does what it has been doing long before the first living thing appeared. It shines. And in that light, at different distances from its fire, 8 worlds have lived their completely different lives. Let us meet them. We will start with the ones closest to the fire, the ones burned most severely, the inner, rocky worlds. And the first in line is the smallest, fastest, and most scorched of them all, Mercury. But keep this question in mind as we go. If all 4 rocky planets got the same ingredients, why did only one of them end up alive? Mercury is the closest planet to the Sun. Its average distance is roughly 36 million miles, a little over a third of the distance from Earth to the Sun. A year on Mercury lasts just 88 Earth days. It circles the Sun faster than any other planet. The ancients named it after the swift-footed messenger god, and the name turned out to be remarkably fitting. But for all its speed in orbit, Mercury rotates around its own axis extraordinarily slowly. One rotation takes roughly 59 Earth days, and here is where things get unusual. Mercury is locked in what is called a 3-to-2 spin-orbit resonance. For every 2 trips around the Sun, it completes exactly 3 rotations on its axis. The result is that a solar day on Mercury, the time between one sunrise and the next, lasts 176 Earth days, nearly half an Earth year. At certain longitudes on Mercury, an observer would witness an astonishing sight. The Sun rises above the horizon, pauses, begins moving backward, pauses again, and only then continues its path across the sky. A double sunrise. This happens because at certain points in the orbit, Mercury's orbital motion outpaces its rotation, and the Sun's apparent motion temporarily reverses. Mercury has essentially no atmosphere. It has what is called an exosphere, a vanishingly thin layer of sodium, potassium, calcium and hydrogen atoms that are constantly knocked off the surface by the solar wind and micrometeorite impacts, briefly hovering above the planet before escaping into space. The density of this layer is so low that its molecules almost never collide with each other. Calling it an atmosphere in any familiar sense is impossible. Without an atmosphere, Mercury cannot redistribute heat. The day side, facing the Sun, heats up to roughly 800 degrees Fahrenheit. The night side cools to roughly -290, a swing of over 1,000 degrees, the most extreme temperature range of any planet in the solar system. On the day side, lead and tin would melt. On the night side, it is colder than the surface of some of Jupiter's moons. And yet, Mercury has water ice. This is one of the most unexpected discoveries in planetary science.
Near Mercury's poles, there are deep craters whose floors never see sunlight. The crater walls are tall enough, and Mercury's rotational axis is nearly perpendicular to its orbital plane, so solar rays never reach those depressions. In these permanently shadowed areas, temperatures stay below roughly -280 degrees Fahrenheit. And there, in eternal shadow on the closest planet to the Sun, radar observations from Earth in the 1990s detected reflections characteristic of water ice. The Messenger mission, which orbited Mercury from 2011 through 2015, confirmed the presence of ice and found that it was covered by a thin layer of dark organic material. The ice was most likely delivered by comets and asteroids. Fire and ice, within a few dozen miles of each other. Geometry and axial tilt are all that separates molten rock from frozen water. Same recipe, same ingredients. Rock, iron, water. Just different conditions. Mercury's surface is covered in craters. If you saw a photograph of Mercury without a caption, you might mistake it for the Moon. The same grey plains, the same impact basins, the same scars from bombardment in the solar system's early ages. The most impressive crater is the Caloris Basin, over 800 miles across. The impact that created it was so powerful that seismic waves travelled through the entire planet and caused chaotic terrain disruption on the opposite side. Imagine punching one side of a clay ball and seeing cracks appear on the other. That is roughly what happened to Mercury. Messenger also found something unexpected. Long scarps, or lobate scarps, crossing the surface for hundreds of miles. These scarps are wrinkles. Mercury is shrinking. As its enormous iron core cools, the planet contracts and the crust crumples like the skin of a drying apple. The planet's radius has decreased by roughly 4 miles since formation, and the process appears to be continuing. Some of the structures Messenger discovered, mysterious shallow depressions called hollows, look geologically fresh. Something on Mercury's surface is still changing. Mercury delivered another surprise. It has a global magnetic field. Weak, roughly 1% as strong as Earth's, but real. For such a small planet, this is remarkable. Mars lost its magnetic field billions of years ago, and Mercury, which is even smaller, somehow kept its. The likely explanation involves the composition of the core. If light elements like sulfur or silicon are dissolved in it, they can sustain convection even in a partially solidified core, keeping the dynamo process alive. Mercury's magnetic field creates a miniature magnetosphere that interacts with the solar wind, complete with a magnetic tail stretching behind the planet. Messenger recorded dynamic magnetic reconnection events in this tiny magnetosphere, essentially the same phenomena that occur in Earth's magnetosphere, only happening 10 times faster because of the smaller scale. Mercury is a natural laboratory for studying magnetic interactions between a planet and a stellar wind. Mercury's core is its defining feature. It is disproportionately huge. It occupies roughly 85% of the planet's radius. For comparison, Earth's core occupies about 55%. Mercury is, in essence, a bare core with a thin shell on top. Why? Several hypotheses compete. A powerful collision early in its formation may have stripped away most of the mantle. The Sun's proximity may have caused lighter silicates to be swept away by solar radiation during accretion. Both factors may have played a role. Data from the Bepi-Colombo mission, a joint project of the European and Japanese space agencies currently on its way to Mercury, should help clarify the picture. And one more detail that builds a bridge from Mercury to the entire history of science. Mercury's orbit precesses slightly. The point of closest approach to the Sun, the perihelion, shifts a little with each orbit. Most of this shift is explained by the gravitational pull of other planets, Jupiter, Venus, Earth. But in the mid-1800s, the French astronomer Urbain Le Verrier discovered that after accounting for all known influences, an unexplained residual remained. 43 arcseconds per century, a tiny amount. But it was real, and it defied explanation within Newtonian gravity. Le Verrier proposed the existence of an unknown planet near the Sun, which he named Vulcan. Astronomers searched for it for decades but never found it. The explanation arrived only in 1915, when Albert Einstein completed his general theory of relativity. In this new theory, gravity is described not as a force acting at a distance, but as the curvature of space-time caused by mass. And when Einstein applied his equations to Mercury's orbit, out fell exactly 43 arcseconds per century. No adjustments, no extra parameters, no hypothetical planets. The geometry of space-time, curved by the Sun's mass, naturally produced the right correction. Einstein later said that when he saw the result, his heart raced for days. Small, scorched, unremarkable Mercury turned out to be the instrument that confirmed one of the deepest revolutions in 20th century physics. Mercury is perhaps the most underestimated planet in the solar system. It is small, inconspicuous, hidden in the Sun's glare, visible from Earth only briefly, low on the horizon, just after sunset or just before sunrise. Many amateur astronomers never see it in their entire lives. Even Copernicus, according to legend, regretted that he never observed Mercury. And yet, this tiny, scorched world taught science lessons far out of proportion to its size. It confirmed general relativity, showed that ice can exist right next to the Sun,
and demonstrated how a planet can shrink over billions of years, wrinkling like a drying apple. Now let us move from Mercury to the second planet from the Sun. And here the story shifts from severe but relatively straightforward, rock, iron, heat, cold, to something far more dramatic. Because Venus is a planet that started out almost the same way Earth did and ended as a nightmare. Venus is nearly the same size as Earth. Its diameter is roughly 7,500 miles, only 5% smaller than Earth's. Its mass is roughly 82% of Earth's. Density and surface gravity are close to Earth's.
If you stood on Venus, you would weigh almost the same as you do at home. By these numbers, Venus is the closest analogue to Earth in the solar system. It is sometimes called Earth's sister, and by the numbers, the name is justified. But that is where the resemblance ends. Venus's surface is heated to roughly 870 degrees Fahrenheit. That is hotter than Mercury, even though Venus is nearly twice as far from the Sun. The temperature on Venus is enough to melt lead, tin, and zinc. Atmospheric pressure at the surface is 92 times Earth's. That is equivalent to the pressure roughly 3,000 feet beneath the surface of Earth's ocean. The atmosphere is 96% carbon dioxide, with clouds of sulfuric acid, and it is so dense that visibility on the surface is limited to a few miles, light barely penetrating the thick, toxic, broiling air.
The Soviet Venera landers are the only spacecraft to have ever made soft landings on Venus's surface and transmitted data from it. Venera 9 and Venera 10 in 1975, Venera 13 and Venera 14 in 82. Surface conditions destroyed them within about an hour, sometimes faster. The photographs they managed to send back show a flat, debris-covered landscape under a dim, orange-yellow sky. Rocks, cracks, flat slabs. No liquid water, of course. At 870 degrees, water cannot exist in any form except vapor, and at 92 atmospheres of pressure, even vapor behaves differently from what we are used to. Why did Venus become this way? After all, it received the same ingredients from the same protoplanetary disk. Rock, iron, water, carbon, nitrogen, the same package that Earth got. The answer is the greenhouse effect, but not the ordinary kind. The runaway kind.
Picture early Venus, a young planet, freshly formed from the protoplanetary disk. It sits a bit closer to the Sun than Earth, an average distance of about 67 million miles versus 93 million for Earth. That gap means Venus receives roughly twice as much solar energy per unit area. In the early stages, when the Sun was dimmer, Venus may have been a tolerable place. There are models that allow for liquid water on early Venus's surface, possibly even oceans. We do not know for sure, but we cannot rule it out entirely. But as the Sun slowly brightened, Venus crossed a critical threshold. Surface temperature began to rise, water began to evaporate, and water vapor is a powerful greenhouse gas, one of the most potent. More evaporation meant more water vapor in the atmosphere, which strengthened the greenhouse effect, which raised temperatures further, which caused more evaporation. A positive feedback loop, a self-amplifying cycle that eventually boiled all the oceans, if they existed, and turned all the water into atmospheric vapor. But the story did not end there. Water vapor in the upper atmosphere was broken apart by the Sun's ultraviolet radiation. Water molecules split into hydrogen and oxygen. The lightweight hydrogen escaped into space, its speed at the high temperatures of the upper atmosphere exceeding Venus's escape velocity. The oxygen reacted chemically with surface rocks. Water was not just evaporated, it was destroyed, disassembled atom by atom, and dispersed. Venus lost its water irreversibly. Meanwhile,
volcanic activity continued releasing carbon dioxide into the atmosphere. On Earth, carbon dioxide partially dissolves in the oceans and gets locked into carbonate rocks, limestones, marbles, through a process called chemical weathering. This process acts as a thermostat, preventing carbon dioxide from accumulating out of control. But on Venus, the oceans were already gone. Carbon dioxide had nowhere to go. It accumulated in the atmosphere, amplifying the greenhouse effect to catastrophic levels. 92 atmospheres of pressure and 870 degrees, the final result of this runaway spiral. Notice the logic. No single cause killed Venus, a whole chain. Too much solar energy triggered evaporation, evaporation triggered the greenhouse effect destroyed the water. Losing the water removed the planet's geochemical thermostat, and without the thermostat, carbon dioxide accumulated until it created the atmosphere we see today. Each link pulled the next. And here is a detail worth reflecting on. The total amount of carbon dioxide in Venus's atmosphere is enormous.
But if you took all the carbon locked in Earth's carbonate rocks, all the limestones, all the marbles, all the chalk cliffs, all the coral reefs, and released it back into the atmosphere as carbon dioxide, you would get an atmosphere remarkably similar to Venus's in mass and composition. Earth and Venus contain roughly the same amount of carbon. The difference is where that carbon is stored. On Venus, it is in the atmosphere as gas, sustaining a greenhouse inferno. On Earth, it is in rocks, hidden by ocean chemistry and geological processes. If Earth lost its oceans, the carbonate rocks would decompose from the heat. The carbon dioxide would return to the atmosphere, and we would get Venus. They are the same planet, with the same amount of carbon. The carbon just sits in different places. Venus rotates around its axis extraordinarily slowly, one rotation every 243 Earth days, and it rotates in the opposite direction from most other planets. The Sun on Venus rises in the west and sets in the east. The cause of the retrograde rotation is not fully understood. A massive collision early in formation may have flipped the rotation axis. Gravitational interaction between the dense atmosphere and solar tides may have gradually reversed the planet. The question remains open. There is one more Venus mystery worth mentioning. In 2020, a team of astronomers announced the possible detection of phosphine in the upper layers of Venus's atmosphere. Phosphine, a molecule of phosphorus and hydrogen, is not produced by known abiotic mechanisms on rocky planets in significant quantities. On Earth, it is produced by anaerobic microorganisms. Could there be life in the clouds of Venus? Microbes floating in that relatively mild layer at an altitude of 30 to 40 miles, where temperatures hover around 70 to 80 degrees Fahrenheit and pressure is roughly 1 atmosphere.
Subsequent reanalyses cast doubt on the detection itself, suggesting the signal might have been an artifact of data processing. The debate continues, and no definitive answer exists yet. But the fact that this question is being discussed seriously tells us something. Venus is not a dead, boring world. It is full of mysteries, and new missions may radically change our understanding. Radar mapping of Venus, first from Earth, then from orbital spacecraft, most notably the Magellan mission in the early 1990s, revealed that beneath the clouds lies a world covered in volcanic plains, cut by long fractures, dotted with shield volcanoes. Some larger than any volcano on Earth. There are signs that volcanic activity continues even today. Data from the European Venus Express orbiter suggest possible surface changes in some volcanic regions over recent decades.
New missions.
NASA's Veritas and Da Vinci Plus, Europe's Envision, are planned for the coming years and promise to give us the most detailed portrait yet of this scorching world. Now let us leave the fire of the inner planets and turn to the pair that concerns us the most. Two worlds that started their journeys remarkably alike, with atmospheres, with volcanoes, possibly with oceans, but diverged in completely different directions. One kept everything needed for life. The other lost nearly everything. Earth and Mars. Two results of the same experiment, separated by one simple factor: size. And here is the question that should stay with you through the next chapter. We said that the difference between Venus and Earth was distance from the Sun, roughly 26 million miles. The difference between Earth and Mars is something else entirely. Mars had the right distance. Mars was not too close. Mars should have been fine. So what went wrong? Of all the pairs in the solar system, Earth and Mars may be the most dramatic. Because this is not about abstract planetary science. It is about why we exist and why Mars does not. Why one planet has flowing rivers and growing forests, while the other is a rusty desert where the atmosphere is so thin that water cannot remain liquid on the surface. Mars is only about 34 million miles from Earth at its closest. By cosmic standards, that is around the corner. Light covers that distance in roughly 3 minutes. And yet, conditions on these two worlds differ so drastically that a human standing on the surface of Mars without a spacesuit would die within a minute, from suffocation, from decompression sickness, from freezing. Let us start with what they have in common, because there are more similarities than you might think. Both planets formed in the inner part of the protoplanetary disk, on this side of the frost line. Both are made mainly of silicate minerals and iron. Both have, or had, an iron core. Both had active volcanism in their early stages. Both received atmospheres from volcanic gases and possibly from volatile compounds delivered by comets and asteroids. And both, by all available evidence, once had liquid water on their surfaces. For Earth, the presence of water is obvious. 71% of the surface is covered by oceans. For Mars, the evidence comes from dozens of space missions conducted over the past half-century. On the surface of Mars, you can see dried-up river channels, deltas, sedimentary deposits, minerals, clays, sulfates, that form only in the presence of liquid water. Orbital spacecraft have found polar caps made of water ice and frozen carbon dioxide. Rovers have found rounded pebbles smoothed by flowing water and chemical traces of salty lakes. Everything points to the conclusion that 3 to 4 billion years ago, Mars was a different world. Warmer, wetter, with a denser atmosphere, possibly with lakes, rivers, and a shallow ocean in the northern lowlands. So what happened? The answer begins with size. Mars is small. Its diameter is roughly half of Earth's, about 4,200 miles. But diameter is only the beginning. The mass of Mars is just 1/10 of Earth's. It is significantly lighter. And this fundamental difference triggered a chain of consequences, each one bringing the planet closer to the state we see it in today. The first consequence of low mass is weak gravity. The escape velocity from Mars's surface is roughly 3 miles per second. Earth's is 7. This means gas molecules in Mars's atmosphere can much more easily reach the speed needed to leave the planet, especially light molecules, hydrogen and helium. But at sufficiently high temperatures in the upper atmosphere, even heavier molecules, oxygen, nitrogen, carbon dioxide, can slowly leak away. The process is unhurried, but over billions of years, it accumulates. The second, and possibly more important consequence, is the loss of the magnetic field. This
is where the story of Mars goes from sad to genuinely tragic. Earth has a global magnetic field. It is generated by convection of molten iron in the outer core, a process physicists call the geodynamo. Liquid iron flows. Earth's rotation twists those flows, and the result is a magnetic field that wraps around the entire planet. This field creates the magnetosphere around Earth, an invisible shield that deflects most of the solar wind. Charged particles streaming from the Sun hit the magnetosphere and flow around it. Only a small fraction gets through, funneled toward the poles where it creates the auroras. Without this shield, the solar wind would crash directly into the upper atmosphere and gradually blow it into space. Mars once had a magnetic field too. We know this thanks to the Mars Global Surveyor mission, which in the late 1990s discovered patches of strong residual magnetization on Mars's surface, mostly in ancient rocks of the southern hemisphere. These patches are magnetized so strongly that the rocks must have cooled and solidified in the presence of a powerful global magnetic field. At some point, Mars had a working dynamo. At some point, its core was hot enough and mobile enough to generate a magnetic field strong enough to protect its atmosphere. But then the dynamo stopped, roughly 3 to 4 billion years ago by current estimates. Why? Most likely because of that same small size. A small planet cools faster than a large one. Mars's surface area to volume ratio is larger than Earth's, so heat escapes faster. Mars's iron core cooled, convection slowed or stopped, and the magnetic field died. Without a magnetic field, Mars was left defenseless against the solar wind. The MAVEN mission. Mars Atmosphere and Volatile Evolution, launched by NASA in 2013 and arriving at Mars orbit in 2014, was designed specifically to study this process. And what it found confirmed the picture with striking clarity. The solar wind is, right now, at this moment, carrying Mars's atmosphere away into space. The rate of loss is roughly a quarter pound per second. Every second, Mars loses a quarter pound of atmosphere. And it has been doing this for billions of years. MAVEN allowed scientists to extrapolate backward, estimating how much atmosphere Mars lost over its entire history. The results indicate that the bulk of the original atmosphere was carried away by the solar wind combined with other escape mechanisms: photochemical escape, sputtering, ion pickup. Mars may once have had atmospheric pressure comparable to Earth's, or at least half of it, enough to support liquid water on the surface. But without a magnetic shield, that atmosphere gradually dispersed. Pressure dropped. Water on the surface could no longer stay liquid. At pressures below a certain threshold, it either freezes or evaporates directly, skipping the liquid phase entirely. Mars dried out. Lakes froze or evaporated, rivers stopped. The planet became what we see today, a cold red desert with surface pressure less than 1% of Earth's. This is one of the most poignant stories in planetary science. Mars is not just another planet. Mars is an example of what could have happened to Earth had it been a little smaller. Every crater, every dried-up canyon on Mars is a silent witness to a long, patient dying. Not an explosion, not a sudden catastrophe, but a slow, molecule-by-molecule draining. And it continues, right now. Every second, a quarter pound. There is another dimension worth examining. The atmospheres of Mars and Earth had different sources and different histories. The primary atmosphere of both planets, what they received directly during formation from the gas disk, was lost almost immediately, blown away by the solar wind of the young, much more active Sun.
The secondary atmosphere, the one we breathe, formed from volcanic gases, degassing of the mantle, and material delivered by comets and asteroids. Carbon dioxide, water vapor, nitrogen, sulfur compounds. All of this was belched out by volcanoes during the first billion years. Both planets received this secondary atmosphere. The question is, what happened to it afterward? On Earth, water condensed into oceans. Carbon dioxide dissolved in the oceans and was locked into carbonate rocks. Nitrogen stayed in the atmosphere, chemically inert and too heavy to escape. Oxygen appeared much later, when photosynthesizing organisms began splitting water and releasing oxygen as a byproduct.
Earth's atmosphere, the one we breathe. 21% oxygen, 78% nitrogen, is a biological product. Without life, the atmosphere's composition would be completely different, mostly carbon dioxide and nitrogen, like Venus and Mars. Life did not merely appear on Earth, it redesigned the planet, turning carbon dioxide into oxygen, creating the ozone layer, altering the chemistry of oceans and rocks. Earth and life evolved together, each transforming the other. On Mars, nothing like this happened. The atmosphere leaked away before any of these processes could gain traction. If life ever arose on Mars, and the Jezero crater may someday give us the answer, it did not get the chance to reshape the planet. The window of opportunity closed. The Curiosity rover, working in Gale crater since 2012, found chemical evidence in sedimentary rocks at the crater floor of an ancient lake that existed there more than 3 billion years ago.
The lake had fresh water, neutral acidity, and contained minerals and organic molecules that are, in principle, compatible with the existence of microbial life. Curiosity was not looking for life directly. It does not carry the instruments for that. But it proved that conditions for life on early Mars existed. The Perseverance rover, which landed in Jezero crater in 2021, is deliberately collecting rock samples that are planned for return to Earth as part of the Mars Sample Return program. If those samples contain evidence of biological activity, even fossilized microbes, even indirect chemical markers, it would be one of the most important discoveries in the history of science. We do not yet know whether life existed on Mars. We only know that it could have. Now let us look at Earth, the counterexample, because Earth could have ended up like Mars if not for several critically important circumstances. Earth is 10 times heavier than Mars.
Its gravity is significantly stronger, making atmospheric escape much harder. Its core is larger and hotter, and the magnetic dynamo has operated continuously for at least 3.5 billion years. Earth's magnetosphere effectively protects the atmosphere from the solar wind. Water delivered by comets and asteroids early on and released by volcanoes stayed on the surface. Oceans formed and did not evaporate because the distance from the sun was large enough to keep temperatures below boiling. Carbon dioxide released by volcanoes did not accumulate to catastrophic concentrations as it did on Venus, because oceans dissolved it, and chemical weathering locked it into carbonate rocks, creating that geochemical thermostat. There is also the matter of the Moon. Our satellite is not just a pretty object in the night sky. It most likely appeared as the result of a colossal collision in Earth's earliest history. According to the most widely accepted hypothesis, the giant impact hypothesis, roughly 50 to 100 million years after the solar system formed, when Earth was still young, half-molten, covered in a magma ocean, a body roughly the size of Mars slammed into it. This body is conventionally called Theia. The impact was oblique, not head-on, and it launched a vast amount of molten material into Earth orbit, mostly from the mantles of both objects. This superheated cloud of debris gathered in orbit and within thousands or tens of thousands of years condensed into the Moon. The Moon's gravity stabilizes the tilt of Earth's rotational axis, holding it within roughly 22 to 25 degrees over billions of years. Without the Moon, Earth's axis could experience chaotic wobbles, occasionally tilting to 60, 70, even 90 degrees, as may have happened with Mars, which lacks a large, stabilizing satellite. Such wobbles would cause catastrophic climate swings. The Moon also creates tides and is slowly receding from Earth at roughly 1.5 inches per year. And then there is plate tectonics. Earth is the only known planet with full-scale plate tectonics. Earth's lithosphere is broken into large plates that slowly move across the surface, creating mountains, volcanoes, ocean ridges, and deep-sea trenches. Plate tectonics plays a critical role in the carbonate-silicate cycle because it is what returns carbonate rocks buried on the ocean floor back into the mantle, where they melt, release carbon dioxide, which returns to the atmosphere through volcanoes. Without plate tectonics, this cycle would break, and long-term climate regulation would be impossible. Why does Earth have plate tectonics while Venus and Mars do not? This question remains one of the most debated in planetary science. Size clearly plays a role. Mars is too small, its lithosphere too thick and rigid to break into mobile plates. But Venus is nearly identical to Earth in size, and yet it has no plate tectonics. One hypothesis links this to water. On Earth, water present in mantle minerals reduces the viscosity of rock, making the mantle more fluid and facilitating convection. On Venus, which lost its water, the mantle may be too stiff to sustain subduction. If this is correct, then plate tectonics on Earth depends not only on the planet's size, but also on the presence of water in the mantle. Water is not just a surface coating. It permeates the entire geology of the planet, down to depths of hundreds of miles, determining the mechanical properties of rock and ultimately the very possibility of tectonics. Another example of how one ingredient, a simple molecule of 2 hydrogen atoms and 1 oxygen atom, determines the fate of an entire planet. Mars does not have plate tectonics. Its lithosphere is a single, unbroken shell. Heat from the mantle escapes differently, through volcanism at fixed points. That is why Mars has Olympus Mons, the tallest mountain in the solar system, roughly 69,000 feet from base to peak, almost 2.5 times the height of Everest. On Earth, volcanoes this enormous are impossible because tectonic plates move over mantle hotspots, not allowing a volcano to grow in one place for too long. The Hawaiian Islands are a chain of volcanoes strung in a line because the Pacific plate drifted over a hotspot. On Mars, the plate did not move. The hotspot stayed put. The volcano grew for billions of years, reaching staggering dimensions. Mars is an archive of its own past. Unlike Earth, where plate tectonics continuously recycles the surface, destroying old rocks and creating new ones, Mars's surface has largely preserved its ancient landscape. Craters formed 3 to 4 billion years ago are still visible. Dried-up river channels from the era when the atmosphere was denser can still be traced in orbital images. Mars is a planet-sized photograph that has captured its own history in terrain and mineralogy. Water on Mars has not disappeared completely. It went underground, froze into permafrost, accumulated in polar caps. Mars's northern polar cap contains substantial reserves of water ice. Subsurface ice has been detected by radar instruments on orbital spacecraft across large areas at mid-latitudes. Mars did not lose all its water, it hid it. Now let us take stock of the inner planets.
4 rocky worlds born from one disk, from one set of ingredients. Mercury, too small and too close to the Sun, scorched and bare. Venus, the right size but too close to the Sun, killed by a runaway greenhouse effect. Earth, the right size, at the right distance, with a working magnetic field and plate tectonics, holding on to water and atmosphere. Mars, too small, cooled too quickly, losing its magnetic field and with it, its atmosphere and water. 4 variations on one recipe. 4 answers to one question. What happens to rock, iron and water if you change the distance from the star and the mass? Notice the symmetry. Mercury and Mars are both small, both lost their atmospheres, both cratered, both showing signs of geological activity that has long since slowed or stopped. But the reasons for their desolation are different. Mercury is too close and too small. Mars has the right distance but is still too small. Venus and Earth are both large, both with substantial atmospheres, both volcanically active. But their atmospheres behave in opposite ways. On Venus, the greenhouse effect spiraled out of control. On Earth, it is held in check by the geochemical thermostat. 2 extreme cases and 2 intermediate ones. 1 survivor and 3, each in its own way, lost. But we have only seen the rocky planets so far, the ones born on this side of the frost line. Small, dense, with solid surfaces, thin atmospheres or none.
4 worlds that, taken together, make up less than 2% of the mass of Jupiter alone. By mass, by volume, by influence on the system's architecture, the rocky planets are small players. The real heavyweights live beyond the frost line. And it is time to cross it and see what happened to the same ingredients on the other side. There, where it was cold enough for ice, where planets accumulated so much mass that they started pulling hydrogen and helium straight from the disk. 2 of the biggest, most powerful, most influential members of the family are waiting for us. Jupiter and Saturn. And their story will rewrite everything we have told so far, because these giants did not simply form and settle onto their orbits. They restructured the system. They migrated. They hurled asteroids and comets at the inner planets. They determined how much water Earth received, and why Mars stayed a runt. If the rocky planets are the product of a meager ration of heat-resistant minerals, the only building material available near the hot sun, then Jupiter and Saturn are the product of a completely different arithmetic. Beyond the frost line, beyond that invisible temperature boundary where water, ammonia and methane froze into solid crystals, the amount of available building material jumped sharply. To the rocky and metallic dust grains was added ice, and there was a lot of it, 3 to 4 times more by mass than the silicates alone. Protoplanets beyond the frost line grew faster and larger, and when their cores reached a critical mass, roughly 10 Earth masses, the tipping point we discussed in Chapter 1 occurred. Runaway gas accretion. The core became so heavy that its gravity began pulling in hydrogen and helium directly from the surrounding disk. And hydrogen and helium are 98% of everything. The planet began growing exponentially, and within a few 100,000 years, it transformed into a gas giant of hundreds of Earth masses. Jupiter is this process taken nearly to its limit. Its mass is roughly 318 times Earth's. Its diameter is roughly 89,000 miles, more than 11 times Earth's. Over 1,300 Earths would fit inside Jupiter, and it is made mostly of hydrogen and helium, the same 2 elements that dominate the Sun and the original interstellar cloud. Jupiter is, in essence, a miniature failed star.
Had it been roughly 80 times more massive, the pressure and temperature in its core would have been enough to ignite thermonuclear fusion, and it would have become a star. Our solar system would have been a binary star system. But it did not happen. Jupiter gathered a lot, but not enough. It remained a planet, the biggest, the most massive, but still a planet. Jupiter's internal structure is radically different from anything we encountered with the rocky planets. Jupiter has no solid surface. Its atmosphere is simply the top layer of a continuously thickening gas. As you descend, pressure and temperature climb. At a certain depth, hydrogen, compressed to monstrous pressures, transitions into an exotic state called metallic hydrogen. It is neither gas nor liquid in the familiar sense. Electrons detach from atoms and move freely, creating a medium that behaves like a liquid metal conducting electricity. It is convection in this metallic hydrogen layer, rotating along with the planet, that generates Jupiter's enormously powerful magnetic field, roughly 20,000 times stronger than Earth's. Jupiter's magnetosphere is so vast that if it were visible to the naked eye, it would appear on the night sky several times larger than the full moon.
At Jupiter's very center, presumably, sits a core of heavy elements, the original icy and rocky seed from which the planet grew. Its mass is estimated at 10 to 20 Earth masses, but we have no direct observations. Data from the Juno mission, orbiting Jupiter since 2016, suggest that the core may be diffuse, spread out rather than compact, as though it had been mixed into the surrounding metallic hydrogen. Perhaps a giant collision with a protoplanet in the early stages of formation stirred the core into the envelope. This is one of many puzzles Juno is helping to solve. Jupiter's atmosphere is a spectacular sight. Cloud bands parallel to the equator are painted in whites, oranges, browns, and reds. The light bands are called zones, the dark ones belts. The color difference relates to chemistry and cloud altitude. Zones are regions of rising currents, where ammonia ice crystals climb higher and look brighter. Belts are regions of sinking currents, where deeper, warmer layers with sulfur and phosphorus compounds show through, giving them their reddish and brown hues. Wind speeds in Jupiter's atmosphere reach hundreds of miles per hour, and convective storms can rival the size of Earth. The most famous feature of Jupiter's atmosphere is the Great Red Spot. It is a giant anticyclone, a storm raging for at least several centuries, possibly much longer. Its size has changed over time. In the 19th century, it was considerably larger than it is now. But at present, it is still wider than Earth. A storm that could swallow our planet, and it has been going for centuries. On Earth, hurricanes lose power when they move over land or cold water. On Jupiter, there is no land, no boundaries, just endless layers of gas, and a storm can persist as long as it is fed by energy from the planet's interior. Jupiter also radiates roughly 1.5 to 2 times more energy into space than it receives from the Sun. Where does this surplus come from? The main mechanism is slow gravitational contraction. Jupiter is still very slowly shrinking, by roughly an inch per year, and the gravitational energy of this contraction converts into heat. Additionally, inside Jupiter, a process called helium rain may be occurring. At certain pressures and temperatures, helium becomes insoluble in hydrogen, forms droplets, and sinks deeper, releasing gravitational energy. This internal heat source plays a crucial role in driving atmospheric dynamics. Jupiter is a planet that is still actively cooling from its formation, and the process will take billions more years. The Juno mission revolutionized our understanding of this planet. Juno found that the cloud bands are not a surface phenomenon, but structures reaching thousands of miles deep. Cyclonic systems around the poles, 5 vortices around the North Pole, and 6 around the South,
are arranged in a remarkably stable geometric configuration that has persisted throughout the years of observation. Gravity measurements allowed scientists to map Jupiter's density at depths of thousands of miles, showing that winds penetrate far deeper than previously thought, to roughly 2,000 miles beneath the cloud tops. And here is something about Jupiter that goes beyond describing one planet and concerns the entire solar system. Jupiter is not just the biggest planet. Jupiter is the architect. Its gravity shaped and continues to shape the structure of the whole system. Start with the asteroid belt. Between the orbits of Mars and Jupiter lies a broad zone populated by millions of rocky and metallic fragments, asteroids.
The total mass of everything in the belt is astonishingly small, roughly 4% of the Moon's mass. That is far less than what you would expect if a full-sized planet had formed in this zone. Why did no planet form here? Because of Jupiter. Its gravity constantly perturbed the orbits of protoplanetesimals in this region, speeding up their relative velocities, turning gentle constructive collisions, where bodies stick together and grow, into destructive ones, where bodies shatter into fragments. Jupiter would not allow the material between Mars and its own orbit to gather into a planet. According to the Grand Tack hypothesis, proposed by Kevin Walsh and colleagues around 2011, the young Jupiter may have migrated inward toward the Sun, passing through the very zone where the rocky planets were forming. In this scenario, Jupiter, while gas still remained in the disk, shifted from 5 astronomical units inward to roughly 1.5, nearly to the current orbit of Mars. Then Saturn, migrating along behind, caught up, and the two giants entered a gravitational resonance that turned them both back outward. Jupiter turned around, like a sailboat making a tack, hence the name Grand Tack. While Jupiter moved inward, it swept material out of the inner disk, scattering and redistributing rocky planetesimals. When it moved back outward, it left behind a depleted zone. And here is what matters. That depleted zone is precisely the region where Mars was forming. If the hypothesis is correct, Mars's small mass, 1/10 of Earth's, is a direct consequence of Jupiter's migration. Jupiter literally robbed Mars of its building material. Mars was destined to be small because a giant came through the neighborhood and took everything the little planet could have grown from. This also connects to Earth's water supply. According to the same model, when Jupiter migrated outward, it mixed material from the inner and outer parts of the disk, flinging water-rich asteroids from beyond the frost line into the inner system. Some of those eventually collided with Earth, delivering the water from which oceans later formed. Jupiter simultaneously robbed Mars and quenched Earth. Then, hundreds of millions of years later, came the second act, the Nice model. Named after the city of Nice, France, where its authors worked. In this model, Jupiter, Saturn, Uranus and Neptune were originally arranged much more compactly than they are today, all within roughly 5 to 15 astronomical units. Beyond them, farther from the Sun, stretched a dense disk of billions of icy planetesimals. Over hundreds of millions of years, the giants slowly exchanged angular momentum with this disk through gravitational interactions. Each time Neptune or Uranus flung an icy body sunward, it received a slight push in the opposite direction, drifting farther out. Jupiter, intercepting those bodies and throwing them onto distant orbits or ejecting them from the system entirely, drifted slightly sunward. At a certain point, Jupiter and Saturn entered a 2-to-1 orbital resonance. Jupiter completed exactly 2 orbits for every 1 orbit of Saturn. Gravitational perturbations stopped averaging out and began accumulating, like pushes on a swing timed to its natural rhythm. The orbits of Uranus and Neptune destabilized. Neptune was flung outward into the dense icy disk through which it tore, scattering billions of comets in all directions. Some were flung onto distant orbits, forming the Oort Cloud and replenishing the Kuiper Belt. Some flew inward toward the Sun, raining down on the inner planets as a bombardment of icy and rocky projectiles. The NICE model is elegant because a single mechanism, the orbital instability of the giants, explains several observed features at once. Neptune's current position far from the Sun, the existence of the Kuiper Belt, the structure of the Oort Cloud, and even some orbital properties of Jupiter's Trojan asteroids. Think about what this picture means. We are used to imagining planets as stable, unchanging residents of their orbits, balls neatly placed in slots on a cosmic shelf. But reality is completely different. The solar system is the product of a chaotic gravitational rearrangement. Jupiter plowed through the inner disk and came back. Neptune was hurled to the edge of the system and wrecked everything in its path. Billions of icy bodies scattered in all directions. The inner planets were showered with debris. What we see today is the quiet after the storm. Stability that emerged after centuries of chaos.
Now let us talk about Saturn, because it deserves its own attention, and not only because of its rings. Saturn is the second largest planet, a gas giant with roughly 95 times Earth's mass. In structure, it resembles Jupiter, a hydrogen-helium envelope, a layer of metallic hydrogen, though thinner than Jupiter's due to lower pressure, and a presumed core of heavy elements. Saturn's density is the lowest of any planet, roughly 0.4 pounds per cubic inch. That is less than the density of water. If a large enough pool existed, Saturn would float in it. Saturn's atmosphere shows a banded structure similar to Jupiter's, but less contrasting. Its cloud colors are more uniform, mostly golden and cream tones. Wind speeds near the equator, however, are extreme, up to roughly 1,100 miles per hour. Periodically, giant storms called Great White Spots erupt, encircling the entire planet, appearing roughly every 30 Earth years. But of course, Saturn's most famous feature is its rings. Saturn's rings are one of the most visually striking structures in the solar system. They extend from roughly 4,000 to 50,000 miles above the planet's cloud tops. Yet their thickness ranges from 30 feet to half a mile. If you shrank the rings to the size of a football field, they would be thinner than a razor blade. The rings consist of countless particles, mostly water ice, with small amounts of rocky dust. Particle sizes range from microscopic specks to boulders several yards across. Each ring particle is a separate, tiny satellite, flying along its own orbit around Saturn. The rings are held together and structured by the gravity of Saturn itself and its many moons. Some small moons, called shepherd moons, orbit along the edges of rings and maintain sharp boundaries through their gravity. The origin of the rings remains debated. For a long time, they were assumed to be as old as the planet itself.
But data from the Cassini mission, which operated in the Saturn system from 2004 through 2017, forced a rethink. The rings' mass turned out to be smaller than expected. Their relative cleanliness, high ice content without significant contamination by interplanetary dust, also points to youth. If the rings had existed for 4.5 billion years, they would have long since darkened from constant micrometeorite bombardment. By current estimates, Saturn's rings may be only 10 to 100 million years old. They may have formed from the tidal destruction of an icy moon that wandered too close to Saturn, or from a collision between two moons. If so, the rings are temporary. In another 100 to 200 million years, they may be gone. We live in an era when Saturn has rings. In a few 100 million years, they may no longer exist. That is a little like living in an era when the moon and the sun appear nearly the same size in the sky. A coincidence that is also temporary, because the moon is gradually drifting away from Earth. Beyond the rings, Saturn has a retinue of more than 140 known moons, and several of them are worlds in their own right. Titan is the second largest moon in the solar system, bigger than Mercury. It is unique in that it possesses a dense atmosphere, the only moon in the solar system that has one. Titan's atmosphere is mostly nitrogen, like Earth's, but at a surface temperature of roughly -290 degrees Fahrenheit, methane plays the role that water plays on Earth. It evaporates, forms clouds, falls as rain, and collects in lakes and seas. The Cassini mission dropped the Huygens probe onto Titan in 2005, the first and so far only landing on a body in the outer solar system. Huygens descended through orange haze, photographing a landscape resembling terrestrial coastlines, dark plains, bright highlands, drainage channels that looked like riverbeds. Radar mapping from Cassini found 3 large seas in the northern hemisphere: Kraken, Ligeia, and Punga, along with dozens of smaller lakes. Kraken Mare is comparable in area to the Caspian Sea. The liquid is a mixture of methane and ethane. Titan is the only body besides Earth where stable liquid bodies exist on the surface, though they are hydrocarbon rather than water. Enceladus is a different story entirely. A small, icy world just over 300 miles across, it could fit comfortably between New York and Pittsburgh. Cassini discovered that from cracks near Enceladus's south pole, called tiger stripes, powerful geysers of water vapor and ice particles blast outward for hundreds of miles. Cassini flew through these geysers and analyzed their composition. The results were remarkable. In addition to water ice and vapor, the plumes contained sodium and potassium salts, evidence of a salty ocean, silicate nanoparticles, evidence of hydrothermal activity on the ocean floor, molecular hydrogen, a possible product of serpentinization, reactions between water and rock at high temperatures, and large organic molecules. Beneath Enceladus's ice shell lies a global salty ocean, heated by tidal forces from Saturn's gravity, and at the bottom of that ocean, there appear to be hot hydrothermal vents. On Earth, deep-sea hydrothermal vents teem with life: worms, mollusks, shrimp, bacteria, all in total darkness, without a single ray of sunlight. If that is possible on Earth, why not on Enceladus?
Enceladus is one of the top candidates for finding extraterrestrial life in the solar system, and its advantage over Europa is that the ocean water shoots itself into space through the geysers. No need to drill through miles of ice, just fly through the plume. Cassini already did this, but its instruments, designed in the 1990s, were not built to search for life. They could not determine whether the organic molecules in the plumes carry signatures of biological activity or are abiotic in origin. For that, a new mission is needed, one with instruments specifically designed to detect biosignatures. Several such missions are at various stages of discussion and development. If even one of them flies, it could answer one of the oldest questions humanity has ever asked. Are we alone? Jupiter's moon system also deserves attention. The 4 largest, Io, Europa, Ganymede, and Callisto, discovered by Galileo in 1610, are 4 completely different worlds. Io, the closest to Jupiter of the large moons, is subjected to monstrous tidal heating. Jupiter's gravity literally kneads it like dough, and the mechanical energy turns into heat. The result? Io is the most volcanically active body in the solar system, with hundreds of active volcanoes and sulfur fountains shooting up to 300 miles high. Europa, the next one out, also experiences tidal heating, but milder. Its surface is an ice shell, beneath which, based on extensive indirect evidence, lies a global salty ocean. Europa is another top candidate for finding life. NASA's Europa Clipper mission is designed for detailed study of this world. Ganymede, the largest moon in the solar system, bigger than Mercury, is the only moon with its own global magnetic field. Its magnetic field suggests a liquid, electrically conductive layer in its interior, possibly a subsurface ocean sandwiched between layers of ice. Callisto, the most distant of the four, appears to be the most geologically inert, its surface densely covered in ancient craters that have not been refreshed in billions of years. Callisto sits far enough from Jupiter that tidal heating barely affects it. It is a witness to the early bombardment, a frozen museum. One recipe: ice, rock, tidal interaction with a giant planet, and four completely different results. Distance from Jupiter, and therefore the strength of tidal heating, determined whether a moon became a blazing volcanic hell, an icy oceanic world, a magnetic giant, or a cratered relic. The same principle as for the 8 planets, only in miniature. Now it is time to move even farther from the Sun, to where the light weakens, temperatures drop, and the 2 remaining giants, Uranus and Neptune, lead their quiet, strange, icy lives. But carry this thought with you. Uranus and Neptune belong to a class of planet, the ice giant, that does not exist in the inner solar system, and it turns out to be the most common type of planet in the entire galaxy. The 2 least studied planets in our system may hold the key to understanding billions of worlds around other stars. When we talk about Jupiter and Saturn, we talk about gas giants, worlds made predominantly of hydrogen and helium, wrapping their massive cores in enormous atmospheres. Uranus and Neptune are different. They are sometimes grouped with Jupiter and Saturn under the heading of giant planets, but in composition and internal structure, they are fundamentally distinct. They are more accurately called ice giants, because the bulk of their mass consists not of hydrogen and helium, but of what planetary scientists call ices: water, ammonia, and methane in various exotic states, compressed to monstrous pressures in the interior. Hydrogen and helium make up only the outer shell, perhaps 15 to 20% of the total mass. Everything else is heavy molecules, squeezed into a hot, dense, electrically conductive fluid. Why did Uranus and Neptune not become gas giants like Jupiter and Saturn? We already discussed this. They formed farther from the Sun, where the protoplanetary disk was thinner and orbital periods were longer. Everything moved more slowly. Their cores grew more slowly. And by the time those cores finally reached enough mass to capture gas from the disk, the gas was already dissipating. The Sun's radiation and solar wind blowing the remaining hydrogen and helium away. Uranus and Neptune were late to the feast. They grabbed some gas, but far less than Jupiter and Saturn did. The result? Planets intermediate in size, roughly 14 to 17 times Earth's mass, far larger than the rocky planets, but 20 times lighter than Jupiter. Uranus is the 7th planet from the Sun, orbiting at roughly 1.8 billion miles. One trip around the Sun takes 84 Earth years.
A person born in the year Uranus, reached a certain point in its orbit, might live an entire life without seeing it return. Uranus was discovered in 1781 by William Herschel, a German musician who emigrated to England and took up astronomy so passionately that he began building his own telescopes, which outperformed the instruments of many professional observatories. Herschel spotted an unusual object in his telescope, not a point like a star, but a tiny disk. He initially thought it was a comet, but the object's orbit turned out to be nearly circular,
and lay far beyond Saturn. It was a planet. The first planet discovered with an instrument rather than the naked eye. The known solar system doubled in size in a single night. The most striking feature of Uranus is the tilt of its rotational axis. The axis is tilted 98 degrees to the plane of its orbit. Uranus essentially lies on its side.
If you picture other planets as spinning tops, standing more or less upright, Uranus is a top that has been knocked over and is rolling along the floor. The consequences of this tilt are extreme. Each pole of Uranus spends 42 years in continuous sunlight, followed by 42 years of continuous darkness. When Voyager 2 flew past Uranus in 1986, the southern pole was aimed almost directly at the Sun, and that entire hemisphere was bathed in light, while the opposite side was plunged into decades of night. The implications for Uranus's climate are unique in the solar system. On Earth, a tilt of 23.5 degrees creates the seasons. On Uranus, with a tilt of 98 degrees, seasons are taken to an extreme. At the peak of polar summer, 42 years of unbroken daylight, the Sun hangs nearly overhead, while the entire other half of the planet is plunged into decades of night. Then Uranus passes through equinox, and both hemispheres briefly receive roughly equal light, like a normal planet. Then the pendulum swings the other way. No other planet experiences such radical seasonal changes. And yet, the temperature difference between the lit and dark sides of Uranus turns out to be surprisingly small. The atmosphere somehow redistributes heat. The mechanism is not fully understood. What tipped Uranus over? The most widely accepted hypothesis is a collision with a large body, roughly Earth-sized or bigger, early in its formation. An impact of that magnitude could have flipped the axis of rotation without destroying the planet itself. Some models suggest not one, but a series of collisions that together produced the current extreme tilt. Interestingly, Uranus's moons and rings orbit in its equatorial plane, meaning they too are tilted along with the planet. This indicates that the collision happened early enough that a disk of materials still existed around Uranus, from which the moons later formed in the new rotational plane. Uranus's atmosphere looks surprisingly bland. In Voyager 2's photographs, it appeared as a uniform bluish-green sphere with almost no visible detail. The color comes from methane in the upper atmosphere. Methane absorbs red wavelengths and reflects blue and green. But later observations with the Hubble Space Telescope and ground-based observatories equipped with adaptive optics revealed cloud bands, storms, and bright clouds of frozen methane. The planet turned out to be less boring than the first flyby suggested. The internal structure of ice giants is one of the most intriguing puzzles in modern planetary science. Models suggest that in the mantles of Uranus and Neptune, at pressures of millions of atmospheres, water behaves in ways completely alien to our experience. It may exist in a so-called super-ionic state, where oxygen atoms form a crystal lattice, while hydrogen atoms flow through it like a liquid. Super-ionic water conducts electricity like a metal, but remains semi-solid mechanically. In Earth laboratories, this exotic state has been produced only for tiny fractions of a second under extreme pressures. But in the interiors of Uranus and Neptune, it may exist permanently, for billions of years, forming a thick layer that plays a role in generating these planets' magnetic fields. The magnetic fields of Uranus and Neptune are themselves a puzzle. Unlike Earth and Jupiter, where the magnetic axis roughly aligns with the rotation axis, the magnetic fields of the ice giants are sharply tilted and offset from the planet's center.
Uranus's magnetic axis is tilted nearly 60 degrees to the rotation axis, and the magnetic center is displaced from the geometric center by roughly a third of the radius. Neptune shows a similar pattern.
This is fundamentally different from the dipole fields of Earth and Jupiter, where the dynamo operates in a deep, liquid metal core. In ice giants, the dynamo apparently sits not in the core, but in the mantle, in that layer of superionic water or conductive mixture of water, ammonia, and methane. There is one more intriguing detail involving methane. At high pressure, deep in the planet, methane molecules break apart, carbon is released, and according to some models, it may crystallize into diamond. Diamond rain in the interiors of Uranus and Neptune. It sounds fantastical, but laboratory experiments conducted since the early 2000s have confirmed that at the pressures and temperatures corresponding to ice giant mantles, methane does indeed decompose with the formation of nanodiamonds. We cannot peer inside these planets to verify, but the physics suggests that deep beneath the bluish-green clouds of Uranus and the blue atmosphere of Neptune, showers of tiny diamond crystals may be drifting slowly toward the core. Neptune is the 8th and most distant planet in the solar system. Its average distance is 30 astronomical units, roughly 2.8 billion miles. Sunlight needs more than 4 hours to reach Neptune. Solar energy arriving at Neptune is less than 1/900th of what Earth receives. At that distance, the Sun looks like a bright star, still dazzling compared to other stars, but no longer the huge, blazing disk we are used to. The story of Neptune's discovery is one of the greatest triumphs of mathematical astronomy. By the mid-1800s, it was clear that Uranus was not moving quite as calculations predicted, even after accounting for the gravity of the Sun, Jupiter, and Saturn. There were tiny deviations that stubbornly resisted explanation. Two mathematicians working independently, John Couch Adams in England and Urbain Le Verrier in France, calculated where an unknown planet would have to be for its gravity to cause the observed perturbations in Uranus's orbit. Le Verrier sent his calculations to the Berlin Observatory, and on September 23, 1846, the astronomer Johann Galle pointed a telescope at the indicated spot and found Neptune within 1 degree of the predicted position, on the very first night of looking. The planet was found not because someone saw it, but because someone calculated it. Mathematics told the telescope where to look. Think about what this means. Two people, sitting at desks with paper and pens, computed the position of an invisible body using only deviations in the motion of another body and a law of gravitation formulated a century and a half earlier. And they were right. This was the moment when Newtonian physics went from being a theory to being something more. A tool of discovery, capable of seeing the invisible. It was also this triumph that prompted Le Verrier to search for the planet Vulcan to explain Mercury's anomaly. And that time, the method failed. Because the anomaly was not caused by missing mass, but by the nature of space-time itself. Two stories, Neptune and Vulcan, together outline the boundaries of Newtonian gravity. Triumph where it works, and failure where Einstein is needed. In size and mass, Neptune is very close to Uranus, slightly smaller in diameter, but slightly more massive, making it denser. Its internal structure is presumably similar, but unlike the pale, nearly featureless Uranus, Neptune turned out to be a surprisingly dynamic world. When Voyager 2 flew past it in 1989, powerful storms were visible on its blue surface, including the Great Dark Spot, an anticyclone resembling Jupiter's Great Red Spot, though smaller. Since then, the great dark spot has vanished, but other storms have appeared and disappeared, evidence of active atmospheric dynamics. Wind speeds on Neptune are the fastest in the solar system, up to roughly 1,300 miles per hour. This is astonishing for a planet receiving so little solar energy. Where does the energy come from? The answer is internal heat. Neptune radiates roughly 2.5 times more energy into space than it receives from the Sun. Something inside the planet is generating heat, most likely slow gravitational contraction and possibly differentiation, the settling of heavier elements toward the center. Uranus, interestingly, has a much weaker internal heat source. It radiates almost exactly as much as it receives from the Sun. This is one of the main differences between the two ice giants, and the reason is not fully clear. The collision that tipped Uranus over may have scrambled its internal structure, disrupting normal convection and slowing heat release. Like twins, one of whom suffered an injury and the other did not. Neptune's largest moon, Triton, deserves a digression. Triton orbits Neptune in the direction opposite to the planet's rotation, a retrograde orbit. Such an orbit is essentially impossible for a moon that formed from a disk of material around the planet. All native moons orbit in the same direction as the planet rotates. A retrograde orbit almost certainly means Triton was captured. It formed somewhere else, most likely in the Kuiper Belt, as an independent icy body similar to Pluto, and was then caught by Neptune's gravity during a close flyby. Triton is probably a close relative of Pluto, both formed in the Kuiper Belt from the same material, roughly the same size. Fate separated them. Pluto stayed free. Triton was captured. Triton is an astonishing world. At a surface temperature of roughly -390 degrees Fahrenheit, it is one of the coldest places in the solar system. And yet, Voyager 2 found active geysers on it, jets of nitrogen erupting from beneath the surface to heights of roughly 5 miles. New missions to the ice giants are being planned. The 2022 Planetary Science Decadal Survey, published by the US National Academies, placed an orbital mission to Uranus at the top of its list of priority flagship missions. Understanding Uranus and Neptune is not just a matter of completing our catalogue of planets. Super-Earths and mini-Neptunes, planets intermediate in size between Earth and Neptune, are the most common class of exoplanets in the galaxy. To understand them, we need to understand Uranus and Neptune, the only representatives of this class in our solar system. Now, planets, even 8 of them, are far from everything the solar system contains. Between them and beyond them lie billions of smaller bodies, asteroids, comets, dwarf planets, icy fragments of the Kuiper Belt, ghostly objects in the Oort Cloud. All of them are leftovers from the protoplanetary disk, pieces of the recipe that did not make it into any of the 8 finished dishes. And their story matters just as much, because it is these leftovers that tell us what the disk was like when everything began. When you cook a meal, there is always something left on the counter: trimmings, crumbs, flour on the surface, vegetable shavings. The protoplanetary disk was no different. The 8 planets took most of the material, but not all of it. Millions of fragments remained, bodies that for various reasons could not grow into full-sized planets. And these fragments are not scattered randomly across the solar system. They are concentrated in specific zones, each of which tells its own part of the story. The first zone is the asteroid belt, stretching between the orbits of Mars and Jupiter, roughly 120 to 330 million miles from the Sun. As we discussed, this region was doomed to remain planetless because of Jupiter's gravitational influence. But its population is far sparser than the name might suggest. When we hear asteroid belt, our imagination conjures a dense cloud of tumbling rocks that you have to dodge your way through,
roughly the way it looks in science fiction movies. In reality, the asteroid belt is almost empty space. Every spacecraft that has passed through it on its way to the outer planets, the Pioneers, the Voyagers, Galileo, Cassini, New Horizons, sailed through without the slightest problem. Average distances between asteroids are measured in millions of miles. The total mass of everything in the belt, as we mentioned, is roughly 4% of the Moon's mass. But what is there is incredibly diverse. Among the asteroids is Vesta, the second largest body in the belt, roughly 320 miles across, a differentiated body with an iron core, mantle, and crust. It is essentially a protoplanet that went through all the stages of planetary formation, heated up, melted, separated into layers, but was stopped in its tracks by Jupiter's gravity before it could accumulate enough mass. The Dawn mission studied Vesta in 2011 and 12 and found on its surface the giant impact basin Rhea Silvia, 300 miles across, nearly as wide as Vesta itself. The impact that created it was so powerful that it ejected roughly 1% of the asteroid's mass into space. Many meteorites found on Earth, the so-called Howardites, Eucrites, and Diogenites, match Vesta's surface composition exactly. Pieces of Vesta sit in museums and laboratories around the world, fragments of a protoplanet knocked loose by impacts millions of years ago and fallen to Earth as meteorites. The largest body in the belt is Ceres, roughly 580 miles across. Ceres is massive enough to have pulled itself into a spherical shape under its own gravity, and it is classified as a dwarf planet. The Dawn mission, orbiting Ceres from 2015 through 2018, found bright white patches in Oort crater that turned out to be deposits of sodium carbonate salt. Their origin is linked to subsurface brine that seeped to the surface through impact fractures. Ceres apparently contains substantial water ice beneath its surface and may once have had an internal ocean. The second zone is the Kuiper Belt, starting at roughly Neptune's orbit, about 2.8 billion miles out, and extending to 3 billion miles and beyond. It is a ring of icy bodies left over from the outer edge of the protoplanetary disk. The most famous Kuiper Belt object is Pluto. Pluto was discovered in 1930 by Clyde Tombaugh at Lowell Observatory in Arizona. It was classified as the 9th planet and held that title for 76 years. But over time, it became clear that Pluto was unusual. It is smaller than the Moon. Its orbit is steeply tilted and noticeably elongated. Its composition, ice and rock, resembles comets more than rocky or gas planets. And starting in the 1990s, astronomers began finding more and more Kuiper Belt bodies similar to Pluto. In 2006, the International Astronomical Union adopted a resolution defining a planet as a body that orbits the Sun, has enough mass to assume a spherical shape, and has cleared the neighborhood around its orbit. Pluto meets the first two criteria, but not the third. It was reclassified as a dwarf planet. In 2015, the New Horizons spacecraft flew past Pluto, and the results exceeded all expectations. Pluto turned out to be a geologically diverse and active world. Sputnik Planitia, a vast basin filled with frozen nitrogen, shows convective cells. Blocks of nitrogen ice slowly rise from the depths, spread across the surface, and sink back down at the edges, renewing the surface over millions of years. Nearby, mountains of water ice rise to 16,000 feet, rigid as rock at those temperatures. New Horizons also found signs of cryovolcanism, volcanoes that erupt not lava, but a mixture of water ice, ammonia, and methane. Beneath Pluto's ice shell, there may be an ocean of liquid water, kept liquid by ammonia, which lowers the freezing point. An ocean on Pluto. on a small icy body beyond Neptune, receiving 1,000th of the sunlight Earth gets.
If this is true, then liquid water in the solar system is not an exception tied to the habitable zone, but something closer to a rule, hidden beneath the surfaces of dozens of bodies. The third zone is the Oort Cloud. If the Kuiper Belt is a ring of icy bodies extending to a few billion miles, the Oort Cloud is a spherical shell enveloping the solar system at distances from roughly 12 billion to 6 trillion miles. 6 trillion miles is roughly 1 light year. The nearest star, Proxima Centauri, is 4¼ light years away. The Oort Cloud extends a significant fraction of the way to the next star. The Oort Cloud has never been directly observed. The objects in it are too small, too distant, and too faint for current telescopes. Its existence is inferred theoretically, based on observations of long-period comets, comets with orbital periods of thousands to millions of years, arriving from all directions in the sky.
The number of objects in the Oort Cloud is estimated in the trillions. Comets are among the most spectacular objects in the solar system, and simultaneously some of the most ancient. Their nuclei, dirty snowballs of ice and dust, are considered nearly unchanged since the solar system formed. When a comet approaches the Sun, ice on its surface sublimates, turning from solid directly to gas, and the gas drags dust particles along, forming a fuzzy coma around the nucleus and 2 tails. A curved dust tail lit by reflected sunlight, and a straight ion tail of ionized molecules pushed directly away from the Sun by the solar wind. Among the asteroids and meteorites, there are also messengers from before the solar system itself.
In certain meteorites, called carbonaceous chondrites, scientists have found microscopic dust grains older than the solar system, pre-solar grains, tiny crystals of silicon carbide or diamond formed in the atmospheres of dying stars and surviving the collapse of our cloud. They were part of the recipe from the very beginning, and they are still here, embedded in rocks you can hold in your hands. In carbonaceous chondrites, scientists have also found amino acids, the building blocks of proteins. The amino acids found in meteorites include both the 20 used by earthly life and dozens of others that earthly life does not use. This is a strong argument for their extraterrestrial origin. Meteorites also contain nucleotide bases, components of DNA and RNA, and sugars including ribose, a key component of RNA. Not life, but the components from which life can assemble, if conditions allow. The OSIRIS-REx mission returned samples from asteroid Bennu in 2023.
The Hayabusa 2 mission returned samples from asteroid Ryugu in 2020. Both asteroids proved rich in organic compounds and hydrated minerals, substances carrying water and carbon, key ingredients for the origin of life. These results strengthened the hypothesis that much of Earth's water and organic material was delivered by exactly such bodies, asteroids and comets that bombarded our planet in its first billion years. The water in your cells, the carbon in your DNA molecules, all of it may have been brought here from the asteroid belt or from beyond the frost line. 66 million years ago, an asteroid roughly 6 to 8 miles across struck what is now the Yucatan Peninsula in Mexico, leaving the Chicxulub crater over 110 miles wide. The consequences: fires, tsunamis, massive ejection of dust and sulfur into the atmosphere, followed by a prolonged impact winter, led to the extinction of roughly 3/4 of all species on Earth, including the non-avian dinosaurs. The solar system has not stopped being a dangerous place. The fragments of the recipe are still flying, but those same fragments also brought us life, or at least its ingredients. Everything is connected. The cloud produced the disk. The disk produced the planets and left behind scraps. The scraps bombarded the planets, delivering water and organic material. Water became oceans. Organics became the building blocks of life. Life evolved for 4 billion years and eventually produced a creature that built telescopes, sent probes to asteroids, and brought back pieces of the very material from which it all began. The circle closes. But before we finish, there is one more chapter.
Because the story of the solar system is not just the story of what was and what is. It also includes the question posed at the very beginning, the one threaded through everything we have discussed. Why this way? Why these worlds? And do other systems exist, with other recipes and other results? Until the mid-1990s, we knew only one planetary system, our own. All of our ideas about how planets form and evolve were built on a single example. That is roughly like trying to understand the laws of cooking after tasting exactly one dish. You can study its ingredients, its temperature, its texture, form hypotheses about why it turned out this way, but without being able to compare it to other dishes prepared under other recipes, you will never know which of your conclusions are universal and which are specific to this one case. Everything changed in 1995 when Michel Mayor and Didier Queloz, working at the Haute-Provence Observatory in southern France, announced the detection of a planet orbiting the star 51 Pegasi. The planet turned out to be roughly half the mass of Jupiter, but it orbited its star in 4 days. 4 days. That meant it sat incredibly close to its star, far closer than Mercury is to our Sun, a gas giant in an orbit where surface temperatures exceed 1800 degrees Fahrenheit. Nobody expected this. No theory of planet formation had predicted it. It was the first of thousands of exoplanets discovered since. The Kepler Space Telescope, launched by NASA in 2009 and operating for nearly a decade, found over 2,600 confirmed exoplanets by watching for tiny periodic dips in the brightness of stars caused by planets crossing or transiting their disks. What we saw overturned our expectations. Planetary systems turned out to be staggeringly diverse. Hot Jupiters, gas giants on tight orbits, turned out to be not uncommon. Super-Earths, planets with masses between 2 and 10 times Earth's, turned out to be perhaps the most typical class of exoplanets. Our solar system has no super-Earths. Between Earth at 1 Earth mass and Neptune at 17, there is a gap. But across the galaxy, super-Earths appear to be more common than any other type of planet. Why we do not have them is an open question, and the grand TAC hypothesis, Jupiter's migration through the inner disk, is one possible answer. Jupiter may have destroyed proto-super-Earths during its pass. The TRAPPIST-1 system, a red dwarf a third the size of our Sun, hosts 7 rocky planets, 3 of them in the habitable zone. All 7 are packed so tightly that the entire system would fit inside Mercury's orbit. The Kepler 16b system has a planet orbiting a binary star, a real Tatooine, where 2 suns rise and set in a complex dance. Systems with tightly packed planets on resonant orbits, systems with multiple gas giants, systems with planets on wildly elongated elliptical orbits, systems where planets orbit opposite to the star's rotation. Each new system is a new recipe, a new set of conditions, a new result. In this context, our solar system, with its neatly arranged rocky planets close to the star and gas giants far away, with nearly circular orbits, with a clean separation along the frost line, looks, if not unique, then at least not the most typical. We may belong to a particular subclass of planetary systems, characterized by a specific history of migration and stabilization that left the inner system clean and hospitable.
The James Webb Space Telescope, which began scientific observations in 2022, can analyze the atmospheres of exoplanets. When a planet crosses in front of its star, part of the starlight passes through the edge of its atmosphere. Molecules in the atmosphere absorb certain wavelengths, leaving characteristic fingerprints in the spectrum. Water vapor, carbon dioxide, methane, ammonia, each molecule has a unique spectral signature. From these fingerprints, you can determine the composition of a planet's atmosphere from tens or hundreds of light years away. In its first years, JWST detected carbon dioxide in the atmosphere of exoplanet WASP-39b, a hot gas giant, unfit for life, but valuable as a proof of concept. Then came detections of water vapor, sulfur dioxide, and other molecules in the atmospheres of various exoplanets. Each measurement is a small step toward the ultimate goal, detecting, in the atmosphere of a rocky planet in a habitable zone, a combination of gases that is hard to explain without biological activity. Oxygen, together with methane, for instance, is an unstable pair that, without a continuous source, meaning life, would quickly vanish. If we ever find that combination in the atmosphere of a rocky exoplanet in a habitable zone, it will be strong, though not absolute, circumstantial evidence for life. Here is a connection worth making. Oxygen in our atmosphere is a biological product. Without photosynthesis, it would not be there. If an alien astronomer observed Earth using the transit method, they would detect oxygen, methane, water vapor, and ozone in our atmosphere simultaneously, a combination that screams biological activity. We already know how to find these molecules around other stars. The question is just when we will find the right combination on the right planet. Statistical estimates based on Kepler data allow a rough count of how many potentially habitable worlds there might be in our galaxy.
Roughly 1 in 5 Sun-like stars has an Earth-sized planet in the habitable zone. The Milky Way contains hundreds of billions of stars. If even 20% of Sun-like stars have a potentially habitable planet, we are talking about billions of such worlds in our galaxy alone. Whether they are actually habitable depends on the full range of factors we have discussed tonight. Does the planet have a magnetic field? Does it have plate tectonics? Is its mass sufficient to hold an atmosphere? Did a nearby giant rob it of building material? Did a runaway greenhouse effect take hold? Every variable that determined the fate of each of the 8 worlds in our system operates out there too. The habitable zone is necessary, but far from sufficient. A planet can sit at the perfect distance from its star, but if it lacks a magnetic field, its atmosphere will be stripped, like Mars's. If it lacks plate tectonics, the carbon thermostat will not work.
If it has too little water, geochemical cycles will stall. If too much, the entire surface may be under a miles-deep ocean. Each of these factors we have seen in action on our neighbors. Venus, a planet without a thermostat. Mars, a planet without a shield. Mercury, a planet without an atmosphere. Earth, a planet where all the factors aligned. And now we can search for these same factors among billions of exoplanets, asking the same question we asked when studying our own system. Did conditions converge enough for the recipe to produce life? We may get the answer within our lifetime. JWST is already analyzing the atmospheres of rocky exoplanets in habitable zones. The next generation of telescopes, ground-based giants with mirrors 100 feet across, space observatories designed specifically for studying Earth-like atmospheres, may in the coming decades find a gas combination pointing to biological activity. Or not find it, which would also be a profoundly important result. Because if it turns out that billions of potentially habitable planets are silent, if life is such a rare event that even under ideal conditions it arises only once in a billion tries, that tells us something deep about the value of what happened here on Earth. Our solar system is not an isolated, self-contained place. The Sun is one of roughly 200 to 400 billion stars in the Milky Way. We sit about 27,000 light-years from the galactic center on one of its spiral arms, the Orion Arm. Together with all the planets, asteroids, comets, and the Oort Cloud, we are moving around the galactic center at roughly 500,000 miles per hour. One lap takes roughly 225 to 250 million years, a span sometimes called the galactic year. In the solar system's lifetime, it has completed roughly 20 such laps. Some researchers suggest that there is not only a habitable zone around stars, but a habitable zone within the galaxy. Too close to the center, and the density of stars, the frequency of nearby supernovae, and the intensity of radiation would make stable planetary systems unlikely. Too far out on the fringes, and there would not be enough heavy elements in the interstellar gas to form rocky planets. We sit in this galactic habitable zone. Not too close, not too far. The solar system is a textbook written by nature, and we are only beginning to read it. Let us return to where we started. One cloud, hydrogen, helium, and 2% of everything else. Oxygen, carbon, silicon, iron. All the ash left behind by earlier generations of stars. The cloud collapsed, spun, flattened into a disk. At the center, a star ignited. Across the disk ran a temperature boundary. Here it is hot, and everything melts except rock, and there it is cold, and water freezes.
On this side of the boundary, 4 small, rocky worlds. Each received roughly the same set of ingredients, but each handled them differently. Mercury, scorched and frozen at the same time, with an enormous iron core and a surface covered in the scars of impacts. Too small and too close to hold an atmosphere, it became an archive, a frozen testament to early epochs, still hoarding ice in the eternal shadow of its polar craters. Mercury's orbit confirmed Einstein's general theory of relativity. A small planet that taught a big lesson. Venus, Earth's sister by size and mass, suffocated by its own greenhouse gases. A world that may once have had oceans, but lost them because it sat a little closer to the sun than it needed to. The runaway greenhouse effect boiled the water. Ultraviolet light broke the molecules apart. Hydrogen escaped to space, and volcanic carbon dioxide accumulated to catastrophic concentrations. 92 atmospheres, 870 degrees.
Venus is a warning about how little it takes to turn a habitable world into a blazing hell. Earth, the only world in our system where the recipe produced life. The right distance from the star, sufficient mass, a working magnetic dynamo shielding the atmosphere from the solar wind, plate tectonics maintaining the carbon thermostat, oceans dissolving carbon dioxide, the moon stabilizing the axial tilt, Jupiter clearing the neighborhood of large impactors, though it may also have delivered our water. A chain of conditions, any of which could have failed, and then this would have been just another dead planet. But they all held, and you lie here, listening to this. Mars, the lost one. Too small, cooled too quickly. The magnetic field died, the solar wind stripped the atmosphere, water retreated underground and froze. Once, rivers flowed there. Once, it may have been habitable.
Now, minus 80 degrees Fahrenheit on average, pressure less than 1% of Earth's, and a quarter pound of atmosphere leaking into space every second. Mars died slowly, patiently, molecule by molecule, over billions of years. On the other side of the frost line, 4 giants. Jupiter, the monster that could have become a star, but did not gather quite enough mass. Its gravity rewrote the architecture of the entire system. Around it, 4 moon worlds, each with its own story. The volcanic hell of Io, the ice-covered ocean of Europa, magnetic Ganymede, ancient Callisto. Saturn, the beauty with rings that may be younger than the dinosaurs. Winds at 1100 miles per hour. Titan with liquid hydrocarbon lakes, the only body besides Earth with open liquid bodies on its surface. Enceladus, with a salty subsurface ocean and geysers launching water vapor into space, carrying molecules that could answer the question of whether we are alone.
Uranus, knocked on its side by an impact 4 billion years ago, pale blue, quiet, the least studied of the 8, hiding exotic ices, superionic water, and possibly diamond rain beneath its blue-green clouds. Neptune, windy, distant, glowing blue from methane, with the fastest winds in the system, internal heat fueling its storms, and a captured moon, Triton, that wandered in from the Kuiper Belt, evidence of gravitational piracy billions of years ago. And around all of this, dust, debris, scraps of the recipe that did not make it into any of the 8 finished dishes. Asteroids storing memories of the first million years. Comets carrying ice that has lain unchanged since the system's birth. Pluto and its kin in the Kuiper Belt. Small, icy worlds existing in silence and darkness at the edge of the sun's influence. And far beyond, the ghostly Oort Cloud. Trillions of icy bodies wrapping the solar system in a spherical shell halfway to the nearest star. All of this, from one cloud,
From one set of ingredients: hydrogen, helium, and 2% of stellar ash. What made the difference? 3 variables. Distance from the sun set the temperature and separated the rocky worlds from the icy ones. Mass determined whether a planet could hold an atmosphere, power a magnetic dynamo, sustain plate tectonics. Time decided whether a core would reach critical mass before the gas disk dispersed, whether a planet's core would cool before its atmosphere could stabilize. 3 variables, 8 outcomes. And one combination, one out of countless possibilities, turned out to be such that on the 3rd planet from the sun, carbon began assembling into molecules, molecules into cells, cells into organisms, organisms into a being capable of looking at the sky and wondering why everything is the way it is. This story is not over. The solar system continues to change, though slowly, far too slowly for us to notice within a single lifetime. The sun is gradually brightening. The moon is inching away from Earth. Saturn's rings are fading. Mars is losing its atmosphere. In hundreds of millions of years, the continents on Earth will fold together again into a single supercontinent, as they have done repeatedly in the past. In 1 billion years, the oceans will begin to evaporate from the sun's increasing brightness. In 5 billion years, the sun will become a red giant, and the habitable zone will shift to Jupiter and Saturn. Enceladus, Europa, Titan, icy worlds sleeping under their shells right now, may briefly thaw and get their chance. And then, a white dwarf, slow cooling, silence. But that is billions of years away. There is time enough. Think about the scale of time. The solar system has existed for 4.5 billion years. Life on Earth for roughly 4 billion. Multicellular organisms for roughly 600 million. Dinosaurs ruled for 165 million years. Homo sapiens appeared roughly 300,000 years ago.
Writing, 5,000 years. The telescope, 400. Spaceflight, under 70. In those 70 years, we sent spacecraft to every one of the 8 planets. We landed robots on Mars and Venus, on the Moon and on an asteroid. We flew past Pluto. We crossed the heliopause, Voyager 1, launched in 1977, with an onboard computer weaker than a pocket calculator, powered by decaying plutonium, is still sending signals from over 15 billion miles away. Its signal takes more than 22 hours to reach us. And it keeps flying, quietly, stubbornly, farther and farther from the Sun, into interstellar space, where the temperature of the cosmic microwave background is roughly 4.5 degrees above absolute zero, and where there is nothing but sparse hydrogen atoms and silence. This entire story, from the collapse of a molecular cloud to Voyager's signal at the edge of interstellar space, is the story of one recipe.
One set of physical laws, applied to one set of ingredients, in an endless variety of conditions. Gravity and temperature, mass and distance, time and chemistry. From these variables, nature has spent 4.5 billion years creating scorched Mercury and icy Neptune, Saturn's rings and Earth's oceans, the volcanoes of Io and the geysers of Enceladus, diamond rain on Uranus and the rusty canyons of Mars. And you, lying here, under a blanket, on the surface of the only one of these worlds where atoms learn to ask questions about themselves. You do not need to remember all the details, the numbers, the names, the distances. They will be here if you want to come back. But if only one thought stays with you, let it be this. Everything you see in the night sky, and everything you are made of, is the same recipe. One cloud, one star, one physics. And an endless diversity of results, depending on where each piece of matter happened to land in that spinning disk 4.5 billion years ago. Let that thought be soft and quiet, like the light of a distant star. It is not going anywhere. It will be here when you wake up. And for now, breathe. The planets are spinning. The sun is burning. Somewhere beyond Neptune, in the silence of the Kuiper Belt, icy boulders slowly tumble in the dark, carrying material 4.5 billion years old. Somewhere in the Oort Cloud, halfway to the nearest star, trillions of icy bodies drift weightlessly, waiting for the gravitational nudge that will someday send one of them falling toward the sun, where it will blaze into a cometary tail and someone on Earth will look up and see it. On Mars, right now, wind is carrying rusty dust through dried-out canyons, and every second another quarter-pound of atmosphere escapes into space. On Jupiter, the great red spot keeps spinning, as it has for centuries, and nobody knows when it will stop. On Enceladus, geysers are erupting from cracks in the ice shell, launching molecules into the void that may carry the answer to whether we are alone. All of this is happening right now, quietly, patiently, without an audience. The solar system does not need you to keep working, but the fact that you can lie here and think about it is perhaps the most remarkable result of the entire recipe. Good night. Everything will be in its place in the morning.